Welcome to the Chill Scientist. Comment your science topic request and we may make a video for you. Let's jump right in. For thousands of years, people looked at the night sky and believed they had identified every wandering star. The only known planets were Mercury, Venus, Mars, Jupiter, and Saturn. They moved differently from the fixed stars, tracing out paths across the sky that fascinated and sometimes confused early astronomers. Beyond Saturn, the heavens seemed to consist only of stars, distant and unchanging. The idea that another planet could be hiding in plain sight simply did not occur to most observers. That makes the discovery of Uranus in the late 18th century such a remarkable turning point in astronomy. Unlike the other planets, which were known since prehistoric times, Uranus was the first planet identified with the aid of a telescope. This alone changed the way people thought about the solar system. It demonstrated that the known planets were not the full extent of our neighborhood, and that scientific tools could expand humanity's view far beyond what the eye alone could detect. The credit for discovering Uranus goes to the German-born British astronomer William Herschel in 1781. Herschel was not working at a royal observatory or with a government-funded team. He was an amateur in the purest sense of the word, a musician by profession who had become fascinated with astronomy and began grinding his own telescope mirrors. His telescopes, handcrafted and carefully polished, were among the best of the age. On the night of March 13th, 1781, while surveying the sky in the constellation Gemini, Herschel noticed a faint bluish object that seemed different from the background stars. At first, he thought he had discovered a new comet. Comets were known to move slowly against the background of stars, and they often appeared fuzzy in telescopes. But careful tracking over the next days and weeks showed that the object did not behave like a comet. Instead of having a tail or moving in a highly elongated path, it orbited the sun in a nearly circular trajectory. This was the behavior of a planet, not a comet. Herschel's careful observations revealed that he had found a new world orbiting beyond Saturn. News of the discovery spread quickly. The scientific community realized the magnitude of what had happened. For the first time since antiquity, the list of known planets had grown. Herschel at first suggested naming the planet Georgium Sidus, or George's Star, in honor of King George III of Britain. This name pleased the king, who rewarded Herschel with a pension that allowed him to devote himself fully to astronomy. But outside Britain, the name was not popular. Astronomers in France, still hostile to George III because of the political tensions of the era, refused to adopt it. Eventually, the name Uranus was proposed by German astronomer Johann Bode. He argued that, just as Jupiter was named after the father of the gods, and Saturn after his father, the new planet should continue the sequence and be named after Uranus, the primordial sky god in Greek mythology and father of Saturn. This suggestion gained broad acceptance, and the name Uranus became standard. It is worth noting that Uranus had been seen before Herschel's discovery, but no one had recognized it as a planet. The earliest recorded observation dates back to 1690, when English astronomer John Flamsteed catalogued it as a star in the constellation Taurus. He even gave it the designation 34 Tauri, not realizing he was misclassifying a planet. Later, in 1750 and 1769, French astronomer Pierre-Charles Lemonnier observed it several times, but he too mistook it for a star. The reason these earlier sightings did not lead to discovery is that Uranus is very faint and moves slowly across the sky. To the unaided eye, it can just barely be visible under excellent conditions, but it looks like a dim star. Only systematic telescopic tracking revealed its true planetary nature. After the discovery, astronomers quickly set about studying Uranus's orbit. The planet is about 2.9 billion kilometers from the Sun, 1.8 billion miles, nearly twice as far as Saturn. This great distance meant that Uranus takes an extraordinary amount of time to complete a single orbit, about 84 Earth years. Because of this, its motion across the sky is very slow. Careful calculations by astronomers such as Bode and others confirmed its orbit, and over the next decades, Uranus was firmly established as the seventh planet of the solar system. The discovery of Uranus also had a major ripple effect on astronomy and mathematics. Over time, careful tracking of Uranus's orbit showed small deviations from what Newtonian physics predicted. These irregularities puzzled astronomers. They seemed to suggest that another, more distant planet might be tugging on Uranus with its gravity. This suspicion led to the mathematical prediction and eventual discovery of Neptune in 1846, a triumph of theoretical astronomy. In this way, Uranus's discovery not only expanded the planetary roster, but also paved the way for yet another breakthrough. For the people of the late 18th and early 19th centuries, Uranus represented the opening of a new frontier. It proved that there was more to the solar system than the 6 planets known since antiquity. It demonstrated the power of the telescope as a tool of discovery, and it inspired astronomers to believe that further surprises might lie beyond. The excitement surrounding Uranus helped fuel a growing movement in astronomy that would eventually lead to systematic searches for asteroids, comets, and trans-Neptunian objects. Today, it may seem strange to think of Uranus as once being confused with a star. Given what we now know about it, we recognize it as a massive planet with rings, moons, and a unique tilted orientation. But in Herschel's time, it was simply a faint speck of light that only stood out because a careful observer tracked it night after night. Herschel's discovery stands as a reminder that even in the age of modern telescopes and spacecraft, attention to detail and persistence can still lead to profound discoveries. The story of Uranus's discovery is therefore not just about one man spotting a faint object in the sky. It is about the way science works: careful observation, testing of hypotheses, debate over names and classifications, and eventually, the building of consensus. It is also about how new tools, like Herschel's telescopes, can suddenly expand the boundaries of what is possible. Just as the invention of the microscope opened up a hidden world of cells and microbes, the telescope allowed astronomers to find an entirely new planet lurking just beyond the reach of the human eye. By the end of the 18th century, Uranus was no longer a mere curiosity. It was a planet in its own right, complete with a mythology-inspired name and a place in the expanding picture of the solar system. This discovery forced scientists to rethink the scale of the solar system and prepared them for the possibility of more discoveries to come. The age of planetary discovery was far from over, but Uranus was the first step into that new era. If there is one feature that makes Uranus instantly stand out from every other planet in the solar system, it is its bizarre orientation. Unlike Earth, Mars, Jupiter, or even Saturn, Uranus is tilted so dramatically that it essentially rolls around the Sun on its side. Its axis of rotation is tipped at about 98 degrees relative to its orbital plane. To put that in perspective, Earth's axis is tilted by just 23.5 degrees, which is enough to give us our familiar cycle of seasons. Saturn, with its gentle lean of about 27 degrees, experiences more dramatic seasons than Earth, but the overall situation is still recognizable. Uranus, however, is an entirely different case. Its equator is almost perpendicular to its orbital path. This means that for half of Uranus's 84-year orbit, one hemisphere is pointed almost directly at the Sun, while the other is plunged into extended darkness. Imagine living on Uranus. For about 42 years, one pole experiences constant daylight, while the opposite pole endures an equally long night. After half a Uranian year, the situation flips, and the other pole gets its turn under the Sun. Near the equator, sunlight comes in at such a shallow angle that the day-to-day cycle of light and dark looks almost sideways. No other planet in our solar system comes close to this extreme. Astronomers have long debated how Uranus ended up in this strange position. The most widely accepted explanation is that Uranus suffered a massive collision early in its history. During the chaotic formation of the solar system about 4.5 billion years ago, planets were constantly bombarded by leftover planetesimals and protoplanets. In this violent environment, it is plausible that a body at least the size of Earth slammed into the young Uranus, knocking it over and leaving it with the extreme tilt we see today. Some models suggest that Uranus may have even experienced more than one such impact, with multiple collisions gradually pushing it into its current orientation. The giant impact hypothesis also helps explain another mystery: the planet's unusual magnetic field. Unlike Earth's magnetic field, which is roughly aligned with its axis of rotation, Uranus's magnetic field is tilted by about 59 degrees from the rotational axis. Moreover, it is not centered within the planet, but offset significantly. A massive collision could have disrupted the interior structure of Uranus in a way that explains this odd magnetic geometry. However, not everyone is convinced that a single giant impact is the whole story. Some researchers have proposed that Uranus's tilt might instead be the result of gravitational interactions with other giant planets, or even with a now lost large moon. In this scenario, Uranus may have gradually rolled onto its side under the combined gravitational tugs of its neighbors without requiring a catastrophic collision. Computer models show that such scenarios are at least possible, though they tend to be less favored than the impact idea. Whatever the cause, the consequences of Uranus's tilt are dramatic. Seasonal changes on Uranus are unlike anything we know on Earth. At the poles, decades of continuous sunlight are followed by decades of continuous night. This extreme seasonal pattern should, in theory, produce violent atmospheric changes. Yet, when Voyager 2 flew past Uranus in 1986, near the time of its southern summer solstice, the planet looked surprisingly bland. Its pale blue-green atmosphere showed very few visible features. This led some scientists to think that Uranus might be a relatively quiet world with less active weather than Jupiter or Saturn. Later observations have complicated that picture. In the decades since Voyager's flyby, the Hubble Space Telescope and large ground-based observatories have been able to track Uranus through different phases of its long seasons. These observations have revealed that Uranus does experience weather with storms, cloud bands, and changing atmospheric activity. The timing of these features seems to be linked to the seasonal cycle caused by the planet's tilt. As Uranus approaches its equinoxes, times when the sun is directly over its equator, its atmosphere appears to become more active. During solstices, when one pole faces the sun, the atmosphere looks calmer. The reason for this is still debated, but it may be related to how sunlight penetrates and warms different regions of the atmosphere at different times. The tilt also affects the way Uranus's magnetosphere interacts with the solar wind. Because the magnetic field is both tilted and offset from the planet's center, as Uranus rotates, its magnetosphere wobbles in a way that is unlike anything seen around other planets. This produces complex and dynamic interactions with charged particles streaming from the sun. For scientists studying planetary magnetospheres, Uranus is a unique and challenging laboratory. Another consequence of Uranus's sideways orientation is the way its rings and moons orbit the planet. The entire system of rings and moons is tilted along with the planet itself, circling around an axis that lies nearly in the plane of Uranus's orbit around the Sun. From Earth's perspective, this means that the appearance of Uranus's rings changes dramatically over the course of its 84-year journey. Sometimes the rings are seen nearly edge-on, and at other times they are spread wide open. The moons, too, trace out unusual paths across the sky relative to the planet. For astronomers, the strange tilt of Uranus raises important questions about planetary formation in general. Was Uranus's sideways rotation a rare accident, or are we simply seeing one example of a process that may be common in other planetary systems? Exoplanet research has revealed that many planets orbiting other stars have eccentric tilts and odd orbital orientations. In this broader context, Uranus may be less of an anomaly than it seems. Its tilt could be a clue that violent impacts, orbital instabilities, and dramatic shifts in orientation are part of the normal life cycle of planets. For students of astronomy, Uranus's extreme tilt is more than just an odd fact. It illustrates the role of chance and chaos in shaping planetary systems. A planet's orientation, something that seems like a basic and permanent trait, can in fact be the result of random events billions of years ago. And that orientation has enormous consequences, shaping the climate, weather, and even the appearance of the planet for billions of years afterward. From a human perspective, the tilt of Uranus is also a reminder of how diverse the planets really are. Our own Earth feels like the baseline for understanding planets, with its moderate tilt, daily rotation, and familiar cycle of seasons. But Uranus shows that the rules we take for granted are not universal. A planet can be knocked sideways, spend decades with one pole in sunlight, and still be a stable member of the solar system. The discovery of Uranus's tilt challenges us to expand our imagination about what planets can be like, both in our own system and beyond. In short, Uranus's sideways spin is not just a curiosity. It is a fundamental part of the planet's identity, influencing its atmosphere, magnetosphere, rings, and moons. It is also a lasting scar from the early violence of the solar system, a visible reminder that planets are not created in calm and order, but in chaos and collision. Uranus holds a unique position in the architecture of the solar system. Lying between Saturn and Neptune, it is the seventh planet from the Sun, orbiting at an average distance of about 2.9 billion kilometers, 1.8 billion miles. That is nearly 20 times farther from the Sun than Earth. Light from the Sun, which takes only about 8 minutes to reach Earth, requires more than 2.5 hours to travel across the gulf of space to Uranus. At such distances, the Sun appears as little more than a bright star in the sky, and the energy available to warm the planet is meager compared with what Earth receives. In terms of size, Uranus is the third largest planet in the solar system, though it is only the fourth most massive. Its diameter is about 50,700 kilometers, 31,500 miles, roughly 4 times the diameter of Earth. That makes it noticeably smaller than Jupiter and Saturn, but still far larger than Earth or Neptune. Its volume is about 63 times that of Earth, meaning that if Earth were hollow, more than 60 Earths could fit inside Uranus. Despite its impressive size, Uranus is less dense than the terrestrial planets. Its mass is about 14.5 times that of Earth, which makes it significantly less massive than Neptune, even though the two are often grouped together as ice giants. The average density of Uranus is only about 1.27 grams per cubic centimeter, slightly higher than that of water. This is much lower than Earth's density of 5.5 grams per cubic centimeter. The low density indicates that Uranus is composed primarily of lighter materials, hydrogen, helium, water, methane, and ammonia, rather than heavy rock and metal. Gravity on Uranus reflects this difference in density. At the cloud tops, surface gravity is about 8.7 meters per second squared, 28.5 feet per second squared. That is only slightly weaker than Earth's 9.8 meters per second squared, 32.2 feet per second squared. This means that if you could stand on a solid surface at the top of Uranus's atmosphere, which you cannot, you would weigh just a little less than you do on Earth. This similarity in gravity, despite the planet's enormous size compared with the Earth, is another consequence of Uranus's lighter composition. The orbit of Uranus is one of the most distant among the classical planets. With a period of 84 Earth years, Uranus takes nearly a human lifetime to make one complete circuit around the Sun. The elongated nature of its seasons, with decades of continuous sunlight or darkness at its poles, is a direct result of this long orbital period combined with its extreme tilt. The eccentricity of Uranus's orbit is relatively modest, meaning its distance from the Sun does not vary as wildly as Pluto's does, but even small changes make a difference when you are so far from the Sun. At its closest, Uranus is about 2.75 billion kilometers, 1.71 billion miles, from the Sun, while at its farthest it stretches out to about 3 billion kilometers, 1.86 billion miles. Its placement between Saturn and Neptune also has gravitational consequences. Uranus's orbit is influenced by the pull of its massive neighbors, and in turn, Uranus's own gravity affects the paths of smaller bodies in the outer solar system. It is situated in a dynamic region where the balance of forces played an important role during the early formation of the solar system. Models of planetary migration, the idea that the giant planets did not form exactly where they are now, but shifted position over time, suggest that Uranus and Neptune may have traded places billions of years ago. In some scenarios, Neptune formed closer to the Sun than Uranus, but was later pushed outward during a period of instability. The location of Uranus also places it within what astronomers call the outer solar system. Beyond the asteroid belt past Jupiter and Saturn lies a realm dominated by giant planets and small icy bodies. Uranus serves as a kind of transitional marker. Inside its orbit, the giants Jupiter and Saturn are often called gas giants because of their thick hydrogen and helium envelopes. Beyond Uranus, Neptune shares its status as an ice giant, but past that lies the Kuiper Belt, home to dwarf planets like Pluto and Eris. Uranus's position is therefore critical to understanding how the solar system is divided and structured. One of the interesting consequences of Uranus's distance and brightness is how faint it appears from Earth. With a magnitude just bright enough to be seen under ideal conditions, Uranus can barely be detected without a telescope. To the unaided eye, it looks like a dim star and is easy to overlook. That is why it eluded recognition for so long, despite being within reach of human sight. Only when Herschel tracked its motion carefully with a telescope did Uranus reveal its planetary nature. Another aspect worth noting is the rotation of Uranus. A day on Uranus lasts about 17 hours and 14 minutes. This is relatively fast compared with Earth's 24-hour day, though not as extreme as Jupiter's 10-hour rotation. However, because Uranus is tipped on its side, its rotation is highly unusual. From the perspective of someone watching from outside the solar system, Uranus essentially spins backward compared with most planets. This retrograde rotation, combined with its tilt, means the planet's orientation and day-night cycles are unlike anything else in the solar system. Uranus's size and mass also affect the behavior of its atmosphere and its ability to hold on to gases. With strong gravity and a thick envelope, Uranus retains lightweight molecules like hydrogen and helium, that Earth would lose to space. This is one of the key differences between terrestrial planets and giants. The ability to accumulate and keep such gases explains why Uranus grew to its current size, while smaller planets like Earth remained rocky. In terms of influence, Uranus's size and gravity are enough to dominate a substantial system of moons and rings. It has at least 27 known natural satellites, along with a set of faint but distinct rings. These orbiting bodies are bound to the planet because of its gravitational pull, which extends millions of kilometers outward. Uranus's hill sphere, the region where its gravity dominates over the Sun's, extends roughly 70 million kilometers, 43 million miles. That is a vast region of space in which Uranus's presence is the controlling factor. For astronomers, Uranus's physical characteristics make it a critical link in understanding giant planets as a whole. Jupiter and Saturn represent one type, massive, osseous, and rich in hydrogen and helium. Neptune and Uranus represent another, smaller, less massive, but containing larger proportions of ices such as water, ammonia, and methane. By comparing Uranus's size, density, and orbital characteristics with those of its neighbors, scientists can piece together the history of how planets of different types formed and evolved. From the perspective of the solar system as a whole, Uranus occupies a spot that is both distant and yet connected. It is far enough out to be cold, faint, and mysterious, but still part of the planetary family that shapes the gravitational structure of the solar system. Its size places it solidly in the category of giants, yet its composition separates it from the gas giants closer in. Uranus is, in every sense, a planet that marks a boundary, one that helps define the variety of worlds orbiting our Sun. Uranus is often called an ice giant, a label that distinguishes it from the larger gas giants Jupiter and Saturn. While Jupiter and Saturn are dominated by hydrogen and helium, Uranus contains a much higher proportion of heavier elements such as oxygen, carbon, nitrogen, and sulfur, mostly in the form of water, methane, and ammonia. These compounds are referred to as ices in planetary science, not because they are necessarily frozen solid inside the planet, but because they are volatile substances that would condense into ice under the cold conditions of the outer solar system. At the very top, Uranus is wrapped in an atmosphere made mostly of hydrogen and helium, with a few percent methane mixed in. This methane is especially important because it absorbs red light, allowing only blue and green wavelengths to be reflected back into space. That is why Uranus appears pale blue or cyan when seen through a telescope. Beneath this thin upper layer, the planet's structure becomes much less certain. Unlike Earth, which has been studied directly with seismology, or Jupiter, which has been probed with spacecraft like Juno, Uranus has not had a dedicated mission to map its interior. Most of what scientists know comes from indirect evidence, gravitational measurements, magnetic field data, and computer models. The best current models divide Uranus into three broad layers: the atmosphere, the mantle, and the core. The atmosphere extending thousands of kilometers deep, consists of hydrogen, helium, and traces of methane and other gases. Below that lies the mantle, which makes up the majority of Uranus's mass and volume. This mantle is not solid rock or liquid water, but a strange, hot, dense fluid made of water, ammonia, and methane under immense pressure. Scientists sometimes call this an ice mantle, though at the temperatures inside Uranus, it behaves more like a hot, slushy ocean of exotic fluids than like ordinary ice. Deeper down, the pressure and temperature rise even higher. Water and ammonia molecules are believed to break apart under these conditions, producing conductive fluids that can generate a magnetic field. It is within this mantle region that Uranus's unusual magnetic field likely originates. Unlike Earth, where the magnetic field comes from a molten iron core, Uranus's magnetism is thought to be produced in this thick shell of conductive ices. This also explains why the magnetic field is both tilted and offset from the planet's center. It is being generated in an irregular, asymmetric region of fluid rather than in a neat spherical core. At the very center of Uranus lies a relatively small rocky core, perhaps about half the size of Earth. Estimates suggest the core may contain silicates, iron, and nickel, compressed to extreme densities. However, compared to the overall size of the planet, this core contributes only a small fraction of Uranus's total mass. The bulk of the planet is made up of the icy mantle surrounding it. One of the ongoing mysteries about Uranus's interior is why it seems to give off so little heat. All the giant planets, including Neptune, radiate more heat into space than they receive from the sun. This excess heat comes from leftover energy from their formation and from slow gravitational contraction. Neptune, for instance, emits more than twice the energy it receives. Uranus, on the other hand, appears to emit almost no internal heat at all. Its thermal emission is roughly equal to the energy it absorbs from the sun, making it the coldest planet in the solar system, despite not being the farthest. Why Uranus is so cold is a puzzle scientists have not yet solved. One possibility is that the giant impact that tilted Uranus may also have disrupted its interior, allowing heat to escape more quickly in the past and leaving it with little energy to radiate today. Another idea is that Uranus's interior structure is layered in a way that prevents heat from it escaping. If the icy mantle has distinct layers of differing composition, convection, the process that carries heat upward, may be blocked, trapping heat deep inside and leaving the outer layers initially cold. Resolving this question will require much more detailed data than scientists currently have. The extreme pressures inside Uranus are difficult to imagine. At depths of tens of thousands of kilometers, pressures may reach millions of times the atmospheric pressure at Earth's surface. Under such conditions, even common molecules behave in exotic ways. Water, for example, may enter a phase called superionic ice, where oxygen atoms form a crystalline lattice, while hydrogen ions move freely through it. This strange form of matter is neither solid nor liquid, as we normally think of them, and it could play an important role in Uranus's interior. If supersonic ice exists within Uranus, it could help explain how the planet's magnetic field is generated. Another intriguing possibility is that Uranus's interior might be a factory for diamonds. Laboratory experiments have shown that under high pressures, methane can break down into carbon and hydrogen, with the carbon crystallizing into diamond. If this process occurs in the deep mantle of Uranus, it could mean that diamond rain is falling inside the planet. These diamonds would not remain as jewels, but would sink into the depths, forming layers or even seas of liquid diamond. While this may sound like science fiction, it is a plausible outcome of the chemistry under extreme pressure. Understanding Uranus's composition is not just about satisfying curiosity. It has implications for planetary science as a whole. Uranus and Neptune are the only two ice giants in our solar system, and planets of similar size appear to be common around other stars. Exoplanet surveys show that planets in the mass range between Earth and Neptune are among the most abundant in the galaxy. By studying Uranus, scientists hope to learn about the internal structures of these widespread exoplanets, which could in turn tell us about how planetary systems form and evolve. Because Uranus has only been visited once by a spacecraft, Voyager 2, in 1986, much of its interior remains speculative. The data we have are good enough to build models, but many uncertainties remain. A future orbiter mission, equipped with instruments to measure gravity, magnetism, and atmospheric composition in detail, could dramatically refine our understanding. Such a mission would not only reveal the secrets of Uranus itself, but also shed light on a whole category of planets that may be the most common type in the universe. In sum, Uranus's internal structure is a complex blend of hydrogen and helium, exotic ices, and a small rocky core. Its mantle, filled with strange high-pressure forms of water, ammonia, and methane, is likely the key to its magnetic field and perhaps to phenomena like diamond rain. The lack of excess heat makes Uranus an outlier among the giants, raising questions about its history and evolution. What seems certain is that Uranus is not just a scaled-down version of Jupiter or Saturn, but a fundamentally different type of world, one that holds clues to the diversity of planets, both in our solar system and beyond. When scientists classify the planets of the solar system, they divide them into two main categories: terrestrial planets and giant planets. Terrestrial planets, Mercury, Venus, Earth, and Mars, are small, rocky, and dense. They have solid surfaces and relatively thin atmospheres. The giant planets, Jupiter, Saturn, Uranus, and Neptune, are much larger, with thick atmospheres and no solid surface to stand on. But within the giant planet category, there is a further distinction. Jupiter and Saturn are called gas giants, while Uranus and Neptune are considered ice giants. This classification reflects a fundamental difference in composition. Jupiter and Saturn are made mostly of hydrogen and helium, the lightest and most abundant elements in the universe. More than 90% of their mass comes from these gases. In contrast, Uranus and Neptune contain much larger fractions of heavier substances, mainly water, ammonia, and methane. These compounds, which astronomers call ices because of how they behave in the cold outer solar system, make up the majority of Uranus's mass. Hydrogen and helium still form the outer layers, but they are only a small part of the whole. The distinction between gas giants and ice giants is not just about semantics. It tells us that Uranus and Neptune formed in different conditions than Jupiter and Saturn. In the early solar system, Jupiter and Saturn grew large enough, quickly enough, to attract massive envelopes of hydrogen and helium before the solar nebula dispersed. Uranus and Neptune, farther out and forming more slowly, did not accumulate as much of these light gases. Instead, they ended up with interiors rich in ices and rock, capped with thinner atmospheres. This difference is reflected in density. Jupiter and Saturn, despite being far more massive, have densities around 1.3 grams per cubic centimeter for Jupiter and 0.7 for Saturn, less dense than water. Uranus, by comparison, has a density of 1.27 grams per cubic centimeter. Neptune is slightly denser still at 1.64. These values indicate a much higher proportion of heavy material inside the ice giants compared with the gas giants. Another key difference lies in energy output. Jupiter and Saturn radiate much more heat than they receive from the Sun. Uranus, as mentioned earlier, radiates almost none. This might be linked to its different internal composition and structure. The way heat moves through layers of hydrogen and helium is not the same as the way it moves through layers of water and ammonia. Understanding the thermal behavior of ice giants is therefore crucial to explaining why Uranus seems so cold. The term ice giant can be misleading, however, because most of the ices inside Uranus are not frozen solids. Deep inside the planet, water, methane, and ammonia exist in exotic, high-pressure fluid states. They may behave more like hot slushes or even form crystalline superionic phases than like ordinary ice. What matters is that Uranus has far more of these compounds than Jupiter or Saturn, which makes its interior a very different environment. From an observational perspective, the icy composition is also evident in the atmosphere. Methane, though only a small fraction of the total, gives Uranus its characteristic blue-green hue. Without methane, the planet would likely appear whitish or yellowish, similar to Jupiter or Saturn. The specific balance of hydrogen, helium, and methane in the upper atmosphere is a visible sign of the differences deeper inside. The ice giant classification has taken on even greater importance with the discovery of exoplanets. Surveys of other star systems show that planets in the size range between Earth and Neptune are extremely common. In fact, they may be the most common type of planet in the galaxy. Some of these worlds are likely rocky super-Earths, while others may be mini-Neptunes, planets with icy mantles and thick atmospheres like Uranus, but smaller. Understanding Uranus helps astronomers interpret this enormous population of exoplanets. If we can figure out the structure and behavior of Uranus, we gain insight into what might be happening on thousands of planets orbiting distant stars. It is also worth noting that Uranus and Neptune are often called planetary twins, but Uranus is the more extreme of the two. While both are ice giants, Uranus is colder, has the more tilted axis, and radiates less heat. Its unique history may have made it the oddball among the ice giants, while Neptune is sometimes considered the more typical representative of the class. Studying the two together provides contrast that helps refine the definition of what an ice giant really is. Finally, the ice giant classification emphasizes that Uranus is not simply a smaller version of Jupiter or Saturn. Its behavior, appearance, and structure are distinct. Its formation was influenced by different circumstances, and its evolution followed a different path. By treating Uranus and Neptune as a separate class, scientists highlight the diversity of planets that exist even within our own solar system. This classification reminds us that the term giant planet covers a spectrum of possibilities, from hydrogen-dominated behemoths like Jupiter to methane-tinted delta worlds like Uranus. In summary, Uranus is an ice giant because of its high proportion of water, methane, and ammonia compared with hydrogen and helium. This makes it fundamentally different from the gas giants Jupiter and Saturn. Its classification matters because it reveals how planets form under different conditions, and because it connects Uranus to the broader population of planets found throughout the galaxy. Far from being a minor detail, Uranus's status as an ice giant is one of the keys to understanding its nature and importance. When someone sees an image of Uranus for the first time, one of the most striking features is its serene blue-green color. Unlike the colorful bands of Jupiter or the rich golden tones of Saturn, Uranus appears almost uniform, as if painted with a soft aquamarine brush. The reason for this distinct appearance lies in the composition of its atmosphere, particularly the presence of methane gas. The atmosphere of Uranus is composed primarily of hydrogen and helium, which are transparent in visible light. If those were the only components, Uranus would appear pale or even nearly colorless, much like Jupiter's upper atmosphere would without its deeper cloud layers. What makes Uranus different is that methane, though only a small fraction of the total atmosphere, about 2%, plays an outsized role in determining what we see. Methane strongly absorbs red light from the sun while allowing blue and green wavelengths to pass through and scatter back into space. This selective filtering creates the planet's turquoise appearance. The exact shade depends on how much methane is present, the thickness of the cloud layers beneath, and the scattering effects of high-altitude hazes. Small variations in these factors can make Uranus appear slightly more blue or more green depending on the lighting and viewing conditions. The structure of Uranus's atmosphere is layered. At the highest levels, around 1 bar of pressure, similar to Earth's sea level, temperatures are extremely cold, dropping to around minus 220 degrees Celsius, minus 364 degrees Fahrenheit. In these layers, methane can condense to form icy clouds. Deeper down, ammonia and hydrogen sulfide are expected to form additional cloud layers, though direct evidence is still limited. Beneath those, at pressures of several hundred bars, water clouds may exist, though these are far below the level that light from the sun can penetrate. One curious aspect of Uranus's atmosphere is how bland it looks compared with the dramatic storms and bands on Jupiter and Saturn. The methane absorption tends to mask deeper contrasts, but there is also less visible cloud activity. For decades, Uranus appeared as a nearly featureless orb in telescopes, only with the arrival of Voyager 2 in 1986 and later observations using the Hubble Space Telescope and ground-based observatories have faint cloud features been detected. These clouds tend to be subtle streaks or small bright spots, often in the mid-latitudes. They suggest that Uranus does have weather patterns, but they are muted compared with the spectacular tempests of its larger cousins. The relative calm of Uranus's atmosphere might be related to its internal heat deficit. Since the planet does not radiate much excess heat, there may be less energy to drive convection and storms. Still, some activity is visible. In the early 2000s, astronomers observed bright storms on Uranus that rivaled some of Neptune's features in size. These outbreaks showed that Uranus is not completely static, and its weather can occasionally become dramatic, especially as the planet approaches equinox and sunlight is distributed more evenly across its surface. High-altitude hazes also play a role in Uranus's appearance. These hazes are likely formed from methane that has been broken apart by ultraviolet light from the sun, a process called photolysis. The fragments recombine into more complex hydrocarbons such as ethane, acetylene, and other compounds. These substances can form tiny particles that create a diffuse haze in the upper atmosphere. This haze can slightly dull the blue-green color, shifting it toward a paler shade. In comparison, Neptune, with less hazy material and possibly more dynamic weather to keep the atmosphere mixed, often appears a deeper blue. Another interesting aspect of methane in the Uranian atmosphere is its role in trapping heat. On Earth, methane is a potent greenhouse gas, far more effective at trapping infrared radiation than carbon dioxide. On Uranus, however, the situation is different. Because of the extreme cold and the dominance of hydrogen and helium, methane's greenhouse effect is limited. Instead, it mainly influences the visible appearance. Scientists studying Uranus's atmospheric chemistry face challenges because of the planet's distance and dimness. Direct measurements are sparse, limited mostly to Voyager 2's brief flyby in 1986. Since then, remote sensing techniques, especially spectroscopy, have been used to identify methane, hydrogen, helium, and traces of other molecules. The possibility of hydrogen sulfide clouds has been supported by recent observations, which would give the deeper atmosphere a distinctive smell if one could somehow experience it directly. An odor often compared to rotten eggs. Comparing Uranus with Neptune is instructive. Both planets owe their blue coloration to methane absorption, but Neptune's deeper color suggests subtle differences in methane concentration or haze thickness. This difference highlights how even small variations in atmospheric chemistry and dynamics can produce noticeable visual effects. For Uranus, the pale aquamarine tint has become its signature, an immediate identifier in images of the solar system. The study of Uranus's atmospheric color is not just about aesthetics. It provides clues about the composition, its temperature, and processes occurring in the planet's outer layers. By analyzing how light is absorbed and scattered, scientists can infer the abundances of gases and the presence of clouds or hazes. These insights are essential for building accurate models of the planet's atmosphere, which in turn help us understand its weather, climate, and evolution. In a broader context, the methane-driven coloration of Uranus also connects to exoplanet research. Many exoplanets detected so far are Neptune-sized worlds orbiting other stars. Understanding how methane shapes the color and spectra of Uranus allows astronomers to interpret observations of distant exoplanets. A planet with methane in its atmosphere may appear blue, giving clues about its composition and temperature even from light years away. In summary, Uranus's blue-green hue comes from methane in its atmosphere, which absorbs red light and reflects blue and green. Beneath this elegant color lies a complex structure of cloud layers, hazes formed by chemical reactions, and occasional bursts of storm activity. While Uranus may seem calm and featureless at first glance, the chemistry of its atmosphere reveals a world shaped by subtle but important processes. Most planets with magnetic fields, including Earth, Jupiter, and Saturn, generate them through a dynamo effect. This occurs when electrically conducting fluids move within a planet's interior, creating self-sustaining magnetic currents. On Earth, this happens in the outer core, where molten iron circulates. On Jupiter and Saturn, the dynamo operates in layers of metallic hydrogen compressed under extreme pressures. For Uranus, however, things are different. Its magnetic field defies easy comparison. Voyager 2's flyby in 1986 revealed that Uranus's magnetic field is neither centered on the planet nor aligned neatly with its rotation axis. Instead, it is tilted by about 59 degrees relative to the axis of rotation and offset by roughly 1/3 of the planet's radius from the center. This makes Uranus's magnetosphere highly asymmetric. If one were to stand near the north pole of the planet, the magnetic field would not be directly overhead. Instead, it would point at a slanted angle, looping oddly across the sky. This strange geometry means the magnetosphere, the bubble of space around the planet dominated by its magnetic field, behaves in unusual ways. As Uranus rotates, the tilted magnetic field sweeps through space like a badly balanced top. The result is a magnetosphere that wobbles dramatically over the course of a day, creating complex interactions with the solar wind. The solar wind, a stream of charged particles from the sun, normally shapes a planet's magnetosphere into a teardrop shape with a compressed side facing the sun and a long tail stretching away. For Uranus, the rapidly changing tilt produces a magneto-tail twisted into corkscrew shapes. The cause of this unusual field likely lies in Uranus's internal structure. Rather than being generated in a deep metallic hydrogen core like Jupiter's, the magnetic dynamo in Uranus may operate in a shallower layer of electrically conducting water, ammonia, and methane under extreme pressures. In this ionic ocean. Water molecules break apart and hydrogen ions move freely, conducting electricity. If the dynamo occurs in a relatively thin shell rather than a large symmetric core, the resulting field could be off-center and oddly tilted. One of the key scientific questions is whether Uranus's strange field is a consequence of its tilted rotation axis or an independent quirk of its interior. The two may be linked. A massive collision early in Uranus's history could have tilted the planet on its side, while also disrupting the internal layers, leaving behind a lopsided dynamo. Alternatively, the field may reflect a natural outcome of how dynamos operate in planets with ice-rich mantles rather than metallic hydrogen interiors. From a practical perspective, Uranus's magnetic field produces auroras, light displays similar to Earth's northern and southern lights. These occur when charged particles from the solar wind funnel along magnetic field lines and strike the atmosphere, causing gases to glow. However, Uranus's auroras are not positioned neatly at the geographic poles. Instead, they can appear at odd latitudes, reflecting the skewed geometry of the magnetic field. They are also generally faint compared with Jupiter's or Saturn's auroras, making them difficult to observe even with powerful telescopes. Understanding Uranus's magnetic field is important not just for planetary science, but also for broader astrophysics. Many exoplanets discovered so far are ice giants, similar in size to Uranus and Neptune. If ice-rich interiors naturally produce unusual magnetic fields, then skewed magnetospheres may be common in the galaxy. This could influence how exoplanets interact with their host stars, how their atmospheres evolve, and even whether they are shielded from stellar radiation in ways similar to Earth. Another intriguing aspect is how Uranus's magnetosphere affects its moons. The magnetic field interacts with the charged particles in the vicinity of the planet, creating radiation belts. These belts can bombard the surfaces of the moons with energetic particles, altering their chemistry and possibly contributing to the reddish or dark coloration observed on some of them. The magnetic environment may therefore play a role in shaping the moon's appearances and surface processes. Despite its importance, our understanding of Uranus's magnetosphere remains incomplete. Voyager 2 provided a snapshot, but only for a short time during its flyby. Since then, observations from Earth have been limited. A future mission orbiting Uranus could map its magnetic field in detail, track how it changes over time, and measure its interactions with the solar wind. This would not only solve lingering mysteries about Uranus itself, but also improve our understanding of magnetic dynamos across the universe. In essence, Uranus's magnetic field is a reminder that nature does not always follow simple patterns. While Earth's magnetic poles wander slowly and Jupiter's field is immense and symmetrical, Uranus offers a skewed, off-center, and constantly shifting example. It challenges scientists to expand their theories of how magnetic fields form and operate in planets with very different interiors. This oddity, far from being a minor curiosity, makes Uranus a crucial test case in planetary magnetism. When people think of planetary rings, Saturn immediately comes to mind with its spectacular, bright and broad bands stretching across the sky. By comparison, the rings of Uranus are much less famous, yet they hold their own scientific intrigue. First discovered in 1977 during a stellar occultation, a moment when Uranus passed in front of a star, and the star briefly dimmed multiple times. The rings were an unexpected revelation. Until then, Saturn was the only planet known to have a ring system. The rings of Uranus are faint, narrow, and dark. There are 13 known main rings, most of them only a few kilometers wide. Unlike Saturn's bright, icy rings, Uranus's are composed of dark particles that reflect very little light. The material may consist of water ice, heavily mixed with darker carbon-rich compounds, which makes the rings appear almost invisible in ordinary telescopes. Voyager 2, during its 1986 flyby, provided the first close-up images, confirming their structure and complexity. One of the most striking features of the Uranian rings is how sharply defined they are. The edges of the rings are crisp, not diffuse, suggesting that something actively maintains their narrowness. Astronomers suspect that tiny moons, often called shepherd moons, play this role. These moons orbit near the rings, using their gravity to corral particles into tight bands and prevent them from spreading out. In fact, two such moons, Cordelia and Ophelia, act as shepherds for Uranus's brightest and outermost epsilon ring. The rings themselves vary in brightness and size. The epsilon ring is the most prominent, measuring about 20 kilometers wide and containing much of the visible material. Others, like the delta and gamma rings, are much narrower. Between the main rings, faint dust bands exist, which may be replenished by micrometeoroid impacts on the moons or the rings themselves. These impacts kick up fine particles that briefly brighten the system before radiation pressure from the sun pushes the dust away. Unlike Saturn's rings, which are billions of years old and possibly as old as the planet itself, Uranus's rings may be relatively young. Some evidence suggests they could have formed only a few 100 million years ago, perhaps from the breakup of small moons. Their dark coloration might result from constant bombardment by radiation and micrometeoroids, which gradually coats the ice with a layer of dark organic material. The rings of Uranus are also unusual in their orientation. Because the planet is tilted on its side, the rings are not aligned in the familiar horizontal plane we see with Saturn. Instead, they circle Uranus vertically relative to the rest of the solar system, creating a striking effect. During solstice, the rings appear edge-on from Earth and are almost invisible. During equinox, when sunlight falls more evenly, the rings are easier to observe. This seasonal effect makes studying them from Earth challenging and requires long-term monitoring. In addition to the main 13 rings, astronomers have detected faint outer rings and diffuse dust sheets. The most distant known ring, discovered in 2005 using the Hubble Space Telescope, lies twice as far from Uranus as the previously known system. This outer ring is bluish in color, unlike the dark inner rings, and is associated with the small moon Mab. Its bluish tint may result from freshwater ice particles being continually supplied by impacts on Mab's surface. The presence of such different rings, some dark and narrow, others faint and diffuse, raises questions about how Uranus's ring system evolved. Did the rings form all at once, or were they created in separate events? Were small moons shattered by impacts, seeding the rings with debris? Or are the rings remnants of material that never coalesced into larger bodies? These questions remain open, and only a dedicated spacecraft mission could provide the detailed answers. From a broader perspective, Uranus's rings help us compare ring systems across the solar system. While Saturn's are massive and icy, Jupiter has faint, dusty rings created by its moons, and Neptune has thin arcs of ring material. Uranus sits in between with narrow but distinct rings that show both dynamical structure and signs of shepherding. Studying all these systems together gives scientists insight into how small particles behave in orbit, how gravity sculpts rings, and how planetary environments recycle material over time. Though not as visually spectacular as Saturn's, Uranus's rings are scientifically fascinating. They remind us that beauty in the solar system comes in many forms, from dazzling broad bands to delicate, almost hidden traces of dust and rock. Their discovery also reshaped our understanding of planets, proving that rings are not unique to Saturn, but a more common feature than once believed. Uranus is accompanied by a fascinating system of moons, with 27 known satellites orbiting the planet. These moons vary widely in sea shape and composition, from large, spherical worlds to tiny, irregular fragments. Collectively, they provide one of the most diverse collections of moons in the solar system. Unlike the mythological gods and heroes that inspired the names of most other planetary satellites, Uranus's moons are named after characters from the works of William Shakespeare and Alexander Pope. This literary tradition gives them distinctive and memorable identities, from Titania and Oberon to Ariel, Umbriel, and Miranda. The five largest moons, Miranda, Ariel, Umbriel, Titania, and Oberon, dominate the Uranian system. They range from about 470 kilometers, 292 miles, in diameter for Miranda to about 1,580 kilometers, 981 miles, for Titania. These moons are large enough for gravity to shape them into roughly spherical forms, and each shows evidence of unique geological processes. While not as massive as Jupiter's Galilean moons or Saturn's Titan, the Uranian moons are geologically intriguing in their own right. Voyager 2's flyby in 1986 provided the only close-up images we have of these worlds. Even with the limited coverage, the spacecraft revealed that they are far from inert. Titania and Oberon display systems of valleys and fault lines, suggesting tectonic stretching of their icy crusts. Ariel has bright surface features that may indicate relatively young ice flows or resurfacing events. Umbriel is darker, with fewer signs of recent activity, but it hosts mysterious bright patches, including a striking ring-shaped feature near one of its poles. Miranda turned out to be the most bizarre of all, with towering cliffs, patchwork terrain, and regions that appear to have been torn apart and reassembled. In addition to the 5 major moons, Uranus hosts a population of smaller inner satellites, many of which act as shepherds for the rings. These moons, such as Cordelia, Ophelia, and Mab, are irregularly shaped and measure only a few tens of kilometers across. They orbit close to the planet, and their gravitational influence helps maintain the sharp edges of Uranus's ring system. Despite their small size, these moons play an essential role in the dynamics of the system. Beyond the major moons and the inner satellites lies a group of irregular outer moons. These bodies, including Sycorax, Caliban, and Prospero, orbit at great distances and follow inclined or even retrograde paths. Their unusual orbits suggest they may have been captured objects, perhaps remnants of icy planetesimals that wandered too close to Uranus in the distant past. If so, they provide clues about the chaotic history of the outer solar system, when collisions and gravitational encounters were far more common. The moons of Uranus are thought to consist mostly of a mixture of water, ice, and rock. Their surfaces are scarred by craters, evidence of countless impacts over billions of years. However, the presence of valleys, cliffs, and resurfaced regions indicates that internal processes have also shaped them. This suggests that some of the moons may once have been warm enough for liquid water to exist below the surface, driven by radioactive heating or tidal flexing from Uranus's gravity. If subsurface oceans ever existed, they would raise intriguing questions about the potential for habitability, even in these distant frozen worlds. The Uranian moons stand out not just for their geology, but also for their naming convention. Titania and Oberon are named after the fairy queen and king from Shakespeare's A Midsummer Night's Dream. Ariel and Umbriel come from Alexander Pope's The Rape of the Lock, while Miranda is from Shakespeare's The Tempest. The smaller moons follow this tradition, bearing names from Shakespeare's plays such as Puck, Sycorax, and Caliban. This literary approach creates a unique connection between planetary science and human culture, blending exploration with storytelling. The discovery timeline of Uranus's moons stretches back centuries. Titania and Oberon were first observed in 1787 by William Herschel, the same astronomer who discovered Uranus itself. Ariel and Umbriel were discovered in 1851 by William Lassell, while Miranda was found in 1948 by Gerard Kuiper. The flood of smaller moons came much later, with many detected only in the late 20th and early 21st centuries. Using powerful ground-based telescopes and the Hubble Space Telescope. Taken together, Uranus's moons form a complex system that reflects both the planet's history and the broader processes of solar system evolution. The large moons bear the marks of geological activity, hinting at warm, dynamic interiors in the past. The small moons shape and maintain the rings, while the irregular outer satellites record a history of captures and collisions. Each group contributes a piece of the puzzle, making Uranus's satellite system one of the most intriguing in planetary science. In many ways, the moons of Uranus remain mysterious. The brief Voyager, 2 flyby, provided tantalizing glimpses, but a dedicated mission is needed to reveal their full stories. Future exploration could determine whether some of them still hide subsurface oceans, what materials compose their surfaces, and how their geologies connect to the broader history of the Uranian system. For now, the 27 moons remain a diverse family of icy worlds orbiting a planet already famous for its own eccentricities. Among all the moons of Uranus, Miranda is perhaps the most fascinating and perplexing. At only about 470 kilometers, 292 miles in diameter, it is the smallest of the 5 major moons, yet its surface looks like a cosmic jigsaw puzzle. When Voyager 2 captured the first close-up images of Miranda in 1986, planetary scientists were stunned by what they saw. Instead of a bland, cratered ice ball, Miranda revealed a chaotic world marked by towering cliffs, strange patchwork regions, and deep canyons unlike anything seen elsewhere in the solar system. One of Miranda's most dramatic features is Verona Rupes, a cliff estimated to be up to 20 kilometers, 12 miles high. This makes it one of the tallest known cliffs in the solar system, dwarfing even the Grand Canyon on Earth. A rock falling from the top of Verona Rupes would take about 10 minutes to hit the ground, though the weaker gravity would make the impact far less catastrophic than on Earth. Still, the sheer scale of this cliff highlights the extreme geological forces that have shaped Miranda. The moon's surface is divided into large, distinct regions called corona. These vast oval-shaped structures are unlike anything seen on most other moons. They appear as patchwork areas, bordered by ridges and valleys, as if giant pieces of terrain were rearranged and stitched back together. 3 major coronae dominate Miranda's surface: Arden, Elsinore, and Inverness. Each has a unique pattern of ridges, troughs, and grooves, suggesting that they formed through intense tectonic or cryovolcanic activity. The presence of these coronae raises major questions about Miranda's history. Why would such a small moon with limited internal heat display such extreme geological features? One possibility is that Miranda once experienced tidal heating caused by orbital resonances with other moons. In such a scenario, the gravitational tug-of-war would have flexed and heated Miranda's interior, driving the surface to crack, shift, and partially melt. If true, this would explain the resurfacing and patchwork terrain. Another hypothesis is that Miranda was shattered by a massive collision early in its history and then reassembled. In this scenario, the coronae could represent regions where blocks of the crust came back together imperfectly, leaving scars and mismatched terrain. The unusual patchwork appearance supports this idea, though it remains uncertain whether such a catastrophic event could explain all the features observed. Miranda also shows evidence of cryovolcanism, or ice volcanism. Some regions appear to have been resurfaced by slushy ice flows rather than molten rock. These ice flows may have emerged from the interior when the crust cracked under stress. Such activity would suggest that Miranda wasn't entirely frozen solid in the past, but instead had a period of internal warmth that allowed ice to move and reshape the surface. The diversity of terrains on Miranda is especially puzzling because small moons typically cool and become geologically inactive fairly quickly. For Miranda to exhibit such dramatic features, something unusual must have occurred. Whether it was orbital resonance, catastrophic impacts, or both, the moon stands as a reminder that even small worlds can surprise us with complex histories. Voyager 2 only imaged part of Miranda's surface during its flyby, leaving much of the moon unseen in detail. What lies on the far side remains unknown. It is entirely possible that even stranger features exist hidden from our view for now. A future orbiter mission to Uranus would almost certainly target Miranda as a high-priority object for study, as it might hold clues about how icy moons evolve under unusual circumstances. Miranda also contributes to the broader story of the Uranian system. Its fractured surface shows how gravitational interactions among moons and the planet itself can generate dramatic geological consequences. If Miranda was once in resonance with Umbriel or Ariel, the tidal heating it experienced could provide a direct link between the dynamics of Uranus's moons and the geology observed today. In terms of naming, Miranda continues Uranus's literary tradition. The moon is named after the daughter of Prospero in Shakespeare's The Tempest. Just as the character Miranda expressed wonder at the brave new world she encountered, the moon, Miranda embodies wonder in the form of one of the solar system's strangest landscapes. Despite its small size, Miranda challenges assumptions about what moons should look like. It reminds scientists that size does not always dictate complexity. Sometimes even the smallest bodies can harbor the most extraordinary stories written across their scarred and fractured surfaces. Of all Uranus's moons, Ariel stands out as the brightest and, in many ways, the most geologically active. At about 1,160 kilometers, 720 miles in diameter, Ariel is the fourth largest of Uranus's moons, slightly smaller than Titania and Oberon, but larger than Miranda and Umbriel. Its bright reflective surface suggests that it is covered in relatively clean water ice, refreshed in places by resurfacing events. This brightness contrasts strongly with the darker surfaces of some of the other moons, making Ariel a particularly striking object in the Uranian system. Voyager 2's images of Ariel revealed a landscape scarred by long valleys, eons, and networks of ridges and grooves. Many of these features appear relatively young in geological terms, with fewer impact craters compared with the more ancient terrains of Titania or Oberon. This suggests that Ariel has undergone resurfacing processes that smoothed and reshaped parts of its crust. The most prominent features are enormous fault valleys known as graben, which form when the crust stretches and breaks. Some of these valleys are hundreds of kilometers long and several kilometers deep, rivaling Earth's largest tectonic features. In addition to tectonic stretching, Ariel shows evidence of cryovolcanism. Some areas appear to have been resurfaced by flows of icy material that once oozed across the surface, similar to lava flows on Earth, but composed of water mixed with ammonia or other volatiles. These cryovolcanic deposits are smoother and lighter in color than the surrounding terrain, marking them as relatively young. The presence of such flows indicates that Ariel's interior was warm enough in the past to allow ice to partially melt and rise to the surface. The likely source of this internal heating was tidal interactions with Uranus and possibly with other moons. Gravitational flexing can generate enough heat to drive geological activity, especially if Ariel was once in orbital resonance with another satellite. While Ariel's interior is probably frozen today, the geological evidence suggests that it was once a dynamic world where stresses and ice flows continually reshaped the crust. One of the most remarkable aspects of Ariel's surface is the abundance of canyons, some with bright deposits on their floors. These bright patches may be the result of fresh ice exposed by landslides, cryovolcanic activity, or even frost deposits. The brightness of these features indicates that Ariel's surface has not been darkened as much by space weathering as other moons, which adds to the impression that it is geologically young compared with many outer solar system bodies. The study of Ariel also provides valuable context for the history of Uranus's moons as a group. Titania and Oberon show signs of tectonics, but their features appear older and less active. Miranda has bizarre patchwork terrain, but on a much smaller scale. Ariel seems to occupy a middle ground, larger than Miranda, more active than Titania and Oberon, and with a surface that tells a story of repeated reshaping. This suggests that the Uranian moons experienced a spectrum of internal heating and activity, with Ariel being one of the most dynamic. Ariel's reflective surface is also significant for understanding its composition. Spectral measurements indicate that water ice dominates, but there may also be traces of carbon dioxide and other compounds. The presence of carbon dioxide is especially intriguing because it may be unstable under current conditions, implying that it was recently replenished or exposed. This raises questions about whether Ariel still has ongoing, albeit minor, geological processes. Despite all that has been learned, much about Ariel remains unknown. Voyager 2 only imaged part of the moon's surface in detail, leaving large regions unmapped. If a future spacecraft were to orbit Uranus, Ariel would be a high-priority target because its young-looking terrain could provide direct evidence of how icy moons evolve under the influence of tidal heating. Understanding Ariel's history could also inform studies of icy exoplanets and moons elsewhere in the galaxy. In naming tradition, Ariel comes from two literary sources. The name appears in Alexander Pope's The Rape of the Lock as a spirit of the air, and in Shakespeare's The Tempest as Prospero's mischievous servant. Both associations are fitting for a bright, active moon that seems full of energy, at least in its past. Ariel reminds scientists that moons are not simply passive satellites. They can be dynamic worlds with tectonics, volcanism, and resurfacing shaped by both internal forces and external gravitational interactions. Among Uranus's moons, Ariel stands out as a world that has clearly been alive with activity, even if that activity has now quieted. In contrast to Ariel's bright, active appearance, Umbriel is a world cloaked in darkness. At about 1,170 kilometers, 727 miles in diameter, it is nearly the same size as Ariel, but its surface could hardly be more different. Umbriel reflects only about 16% of the sunlight that strikes it, making it the darkest of Uranus's 5 major moons. This low reflectivity, or albedo, suggests that its surface is coated with dark, carbon-rich material, perhaps deposited by micrometeoroid impacts, or altered by radiation over billions of years. When Voyager 2 flew past Uranus in 1986, it captured limited images of Umbriel, revealing a heavily cratered surface with relatively few signs of geological activity, unlike Ariel, which shows evidence of resurfacing and tectonics. Umbriel appears to have remained geologically quiet for most of its history. Its ancient crater-scarred terrain indicates that it has not undergone significant renewal for billions of years, preserving a record of impacts stretching back to the early solar system. Despite this apparent inactivity, Umbriel does have some intriguing features. The most notable is a bright ring-shaped patch near its equator, about 140 kilometers, 87 miles, across, informally nicknamed Wunda. This feature appears to be a large impact crater with an unusual bright deposit at its center. The brightness may be due to fresh ice exposed by the impact, contrasting sharply with the dark surrounding terrain. Wunda stands out as a rare splash of light on an otherwise shadowy world, and its existence raises questions about the composition of Umbriel's crust. The origin of Umbriel's dark surface remains a subject of study. One possibility is that it has been coated with dark material ejected from outer irregular moons or captured objects. Another idea is that chemical processes on the surface, driven by the bombardment of charged particles from Uranus's magnetosphere, have gradually altered the ice into darker compounds. Whatever the cause, Umbriel's gloominess sets it apart from its siblings, giving it a distinct identity in the Uranian system. Comparing Umbriel to Ariel highlights the diversity among Uranus's moons. Both are similar in size and likely in overall composition, mixtures of water, ice, and rock. But their surfaces tell different stories. Ariel shows signs of tectonics and cryovolcanism, while Umbriel shows only the scars of impacts. This suggests that internal heating played out differently in the two moons. Ariel may have experienced stronger tidal flexing or retained heat longer, while Umbriel cooled quickly and became geologically inert. Even though Umbriel seems quiet today, it may not have always been so. Models of its interior suggest that it could once have harbored enough heat for limited activity. If so, any signs of tectonics or resurfacing may have been buried under billions of years of impact cratering and surface darkening. Umbriel's apparent stillness may therefore mask a more dynamic past. The exploration of Umbriel remains incomplete. Voyager 2 only imaged about 40% of its surface, and at relatively low resolution. The unseen regions could hold additional surprises, such as valleys, unusual craters, or localized patches of bright material like Wunda. Until a new mission visits Uranus, Umbriel will remain one of the least understood large moons in the outer solar system. Umbriel's name comes from Alexander Pope's The Rape of the Lock, where Umbriel is a dusky, melancholy sprite. The association is fitting. Umbriel is literally dusky, with its dark surface absorbing most of the sunlight that falls on it, and metaphorically melancholy in its seemingly quiet, unchanging state. For planetary scientists, Umbriel is a reminder that not all moons are equally active. Some preserve ancient surfaces that act as time capsules, recording billions of years of bombardment and surface alteration. While Ariel may teach us about geological activity, Umbriel offers a contrasting lesson in planetary dormancy. Together, the two moons show the range of possibilities even among satellites orbiting the same planet. Titania is the giant of the Uranian moon system, measuring about 1,580 kilometers, 981 miles, in diameter. It is the eighth largest moon in the solar system, bigger than all but a handful of planetary satellites such as Ganymede, Titan, and Callisto. Discovered in 1787 by William Herschel, the same astronomer who discovered Uranus itself, Titania has long held a place as one of the most prominent companions of the tilted planet. Despite its size, Titania remains a relatively mysterious world, known mostly through the brief glimpse provided by Voyager 2 in 1986. The surface of Titania is marked by a mix of ancient impact craters and scenes of geological activity. Like the other large moons of Uranus, Titania is composed primarily of a roughly equal mixture of water, ice, and rock. Its density of about 1.71 grams per cubic centimeter suggests a substantial rocky component compared with the pure ice moons of Saturn. This means Titania may have a layered interior with a rocky core and icy mantle, and possibly even a subsurface ocean sandwiched between. If such an ocean exists, it would be kept liquid by residual heat and perhaps antifreeze-like substances such as ammonia. The most striking surface features observed on Titania are its enormous fault valleys, some extending hundreds of kilometers across the moon. These long troughs, or graben, suggest that Titania's crust has stretched and broken apart in the past. Such tectonic features are evidence of internal activity. Perhaps as the moon cooled and its interior contracted, the outer shell cracked and shifted to relieve the stress. Some of these valleys are bordered by steep cliffs, making Titania's landscape rugged and dramatic. One example is Messina Cosmota, a canyon system stretching for about 1,500 kilometers, 930 miles, nearly as long as the entire state of California. This canyon is far larger than the Grand Canyon on Earth, underscoring the scale of tectonic forces that shaped Titania. The presence of such massive features indicates that Titania was not a geologically dead world in the past, but one that underwent significant internal changes. Impact craters also dot Titania's surface, though many appear degraded or modified, suggesting resurfacing processes may have erased or softened some of them. The largest confirmed crater, Gertrude, is about 326 kilometers, 203 miles, in diameter. It features a central dome-like structure, likely caused by the rebound of the crust after the impact. The relative scarcity of very large, pristine craters compared with some other moons hints that Titania's surface has been renewed, at least partially, since its earliest days. The possibility of a subsurface ocean on Titania is particularly exciting. Models suggest that if enough ammonia or salts are present to lower the freezing point of water, liquid layers could survive beneath the icy shell. Such oceans would be buried tens or even hundreds of kilometers down, making them difficult to confirm without direct measurements. Still, if real, they would put Titania in the company of moons like Europa, Enceladus, and possibly Ganymede as candidates for hidden oceans. This raises the tantalizing possibility that Titania a distant moon of Uranus, could harbor environments where life might exist in some form, even if only microbial. Titania's orbit is relatively close to Uranus, at about 400 to 36,000 kilometers, 271,000 miles. Like all of the major Uranian moons, Titania is tidally locked, meaning it always shows the same face to the planet. Its orbit lies within Uranus's magnetosphere, meaning the moon is constantly bombarded by charged particles trapped in the planet's magnetic field. This bombardment may darken the surface over time, contributing to its reddish coloration compared with the brighter, icier Ariel. Despite being the largest moon of Uranus, Titania remains one of the least explored large moons in the solar system. Voyager 2's images covered only part of its surface at moderate resolution, leaving huge areas unmapped. From Earth, Titania appears only as a faint point of light, with few details visible even in the largest telescopes. A dedicated Uranus orbiter, equipped with modern instruments, could reveal whether Titania has an ocean, study its tectonic canyons in detail, and search for ongoing activity, such as venting or resurfacing. The name Titania comes from Shakespeare's A Midsummer Night's Dream, where Titania is the queen of the fairies. The name is fitting for the largest moon of Uranus, majestic in size and presiding over a complex family of satellites. It continues the literary theme that makes Uranus's moons unique in planetary science, linking human imagination with the realities of space exploration. In many ways, Titania embodies the balance between familiarity and mystery. Its surface features hint at geological activity, yet its true history remains only partly written in the data we have. It may hide an ocean beneath its crust, but this remains speculative until future missions provide confirmation. For now, Titania is both the queen of Uranus's moons and a world waiting to reveal its secrets. Oberon, the second largest moon of Uranus, has a diameter of about 1,523 kilometers, 946 miles, making it only slightly smaller than Titania. Like Titania, it was discovered in 1787 by William Herschel, who had already revolutionized astronomy just a few years earlier with his discovery of Uranus itself. Oberon is the outermost of the 5 large classical moons of Uranus, orbiting at a distance of about 584,000 kilometers, 300 to 63,000 miles, from the planet. Its location on the edge of Uranus's inner system gives it a somewhat isolated role compared to its closer siblings, and its surface tells a story of ancient history preserved over billions of years. The surface of Oberon is heavily cratered, even more so than Titania, Ariel, or Umbriel. This makes Oberon the most obviously ancient-looking of the major Uranian moons. Many of its craters are large, with prominent bright rays of ejected material radiating outward. The largest confirmed crater is Hamlet, about 206 kilometers, 128 miles, in diameter. Some craters display central peaks formed when the crust rebounded after massive impacts. The density and preservation of these craters suggest Oberon's surface has seen little in the way of geological resurfacing. Unlike Ariel or Titania, which show signs of tectonic activity and internal changes, Oberon's crust appears to have remained largely frozen and unmodified for most of its history. Still, Oberon does not lack interesting features. Voyager 2's images reveal dark patches inside some of the craters, which may be deposits of fresh material brought up from beneath the surface during impacts. These patches are intriguing because they might represent water ice mixed with darker substances such as carbon compounds, silicates, or ammonia hydrates. If so, impacts on Oberon may provide one of the few ways to glimpse what lies beneath its outer shell. Oberon's overall color is somewhat redder than the brighter Ariel or Titania, likely due to long-term exposure to space weathering and bombardment from charged particles in Uranus's magnetosphere. This radiation darkens and reddens icy surfaces over time. Since Oberon spends most of its orbit beyond the densest parts of Uranus's magnetosphere, its surface aging may also reflect bombardment by micrometeorites from the outer solar system. Being the outermost large moon, Oberon is more exposed to such impacts than its inner siblings. The interior structure of Oberon is probably similar to the other large moons of Uranus, a mixture of roughly equal amounts of water, ice, and rock, giving it a density of about 1.63 grams per cubic centimeter. This suggests a differentiated structure with a rocky core surrounded by icy layers. Some models propose that Oberon, like Titania, might host a subsurface ocean if ammonia or salts are present to lower the freezing point of water. However, the likelihood of such an ocean surviving to today is considered lower, given Oberon's distance from Uranus and its relatively inactive surface. Still, if liquid water exists even in small amounts deep below, it could make Oberon part of the broader conversation about potentially habitable niches in the solar system. Oberon's orbit is notable for being tilted at a significant angle relative to Uranus's equator. This is a consequence of Uranus's extreme axial tilt, which flips the planet sideways compared with the rest of the solar system. As a result, Oberon and the other moons experience seasons unlike anywhere else, with decades of continuous sunlight followed by decades of darkness at their poles. Such conditions influence the thermal cycles of the moon's surface and may affect how volatile materials, such as carbon dioxide ice, migrate over time. Voyager 2's brief encounter with Oberon in 1986 remains the only direct exploration of this moon. The spacecraft imaged less than half of the surface, leaving large regions unmapped. With modern spacecraft capable of high-resolution imaging, spectrometry, and radar probing, Oberon could reveal far more about its composition and history. Unfortunately, it remains out of reach for now, awaiting a future Uranus mission. Oberon is named after the king of the fairies in Shakespeare's A Midsummer Night's Dream. Together with Titania, the queen, the two largest moons of Uranus carry titles that reflect their grandeur and size. The choice of names links human literature with the exploration of space, continuing Uranus's unique tradition of drawing from Shakespeare and Alexander Pope rather than Greco-Roman mythology. As the outermost of Uranus's large moons, Oberon provides a crucial counterpoint to the more geologically active worlds closer in. It is a record of impacts stretching back to the early solar system, with its scarred surface offering a frozen archive of cosmic history. If Titania and Ariel represent moons shaped by internal activity, Oberon stands as the reminder of what happens when a world becomes geologically silent. It has preserved its scars instead of erasing them, keeping a story billions of years old etched into its crust. Despite this quiet exterior, Oberon's significance should not be underestimated. It provides the baseline against which we can compare the other Uranian moons. By understanding why Oberon remained so static while others were more dynamic, planetary scientists can better unravel the forces that drive or halt geological evolution in icy satellites. Its position at the edge of Uranus's system also makes it a natural boundary marker, linking the world of Uranus to the vastness of the outer solar system beyond. In the end, Oberon is not just a frozen relic. It is a key piece of Uranus's story, and by extension, the story of planetary formation and survival in the distant reaches of the Sun's domain. Umbriel is one of the most intriguing moons of Uranus because of its unusual appearance. Among the 5 major satellites of Uranus, Umbriel is the darkest, reflecting only about 16% of the sunlight that strikes it. By comparison, Ariel reflects about 35%. This extremely low reflectivity, or albedo, makes Umbriel stand out in images, even though in size it ranks as the 3rd largest Uranian moon with a diameter of about 1,169 kilometers, 726 miles. Like Titania and Oberon, it was discovered by William Lassell in 1851, the same year he identified Ariel. The name Umbriel comes from Alexander Pope's poem, The Rape of the Lock, where Umbriel is a melancholy spirit of the underworld. It fits the moon's dark and brooding appearance quite well. The most striking feature of Umbriel is its coloration. Its surface is uniformly dark and bluish compared to the other Uranian moons. This has led scientists to propose that Umbriel's surface is coated with a material different from its siblings, perhaps radiation-darkened methane ice, carbon-rich compounds, or deposits from impacts with small, dark outer solar system bodies. Another possibility is that particles from Uranus's magnetosphere bombard Umbriel in a way that alters its icy crust over time, darkening it and giving it its distinct appearance. Because Umbriel lies closer to Uranus than Oberon or Titania, it may be more exposed to charged particles trapped in the planet's magnetic field. Voyager 2 revealed some of the details of Umbriel's surface in 1986, though only about 40% of it was imaged in useful detail. Umbriel is heavily cratered, with few signs of internal activity, such as the valleys, canyons, or fault lines that are visible on Ariel or Titania. This suggests Umbriel has been geologically quiet for most of its history. The largest crater identified on Umbriel is Wokolo, which spans about 210 kilometers, 130 miles. Another major feature is the crater Skind, which shows bright rays of material, probably ejecta from the impact that formed it. But perhaps the most unusual feature of Umbriel is a bright ring, called the Wunda ring, inside a large crater near the moon's equator. This feature is striking because it stands out dramatically against Umbriel's otherwise dark surface. Its origin is not fully understood, but it may represent fresh ice exposed by an impact or perhaps a deposit of material of a different composition. Internally, Umbriel is believed to consist of about 50% water ice and 50% rock, similar to the other major Uranian moons. Its density of 1.39 grams per cubic centimeter supports this estimate. Unlike Titania and Ariel, however, there is little evidence that Umbriel underwent significant internal heating or geological activity that might have reshaped its surface. This lack of resurfacing may explain why Umbriel retains such a high density of old craters compared to Ariel or Titania. If there was ever a subsurface ocean, it is likely long frozen today. Umbriel's orbit places it about 266,000 kilometers, 165,000 miles from Uranus, well within the planet's magnetosphere. This could explain why Umbriel is so much darker than Oberon and Titania, which orbit farther out. Charged particles spiraling along Uranus's magnetic field lines may strike Umbriel's icy crust more heavily, breaking apart molecules and leaving behind darkened residues. Over billions of years, such weathering could have dramatically altered the surface. Another factor may be that Umbriel has a less reflective crust to begin with. If its outer layers contain more carbon-rich material or organics than Ariel or Titania, this would naturally give it a darker tone. It is also possible that Umbriel's dark material was deposited later in its history, perhaps by comets or small Kuiper belt objects colliding with it. Future missions equipped with spectrometers could answer these questions by identifying the specific compounds on Umbriel's surface. In terms of scientific importance, Umbriel provides a valuable contrast to the other Uranian moons. Titania and Ariel demonstrate signs of tectonic or cryovolcanic processes that reshape their surfaces, while Oberon preserves a heavily cratered but somewhat brighter landscape. Umbriel shows what happens when a moon remains geologically dormant while being bombarded by radiation and micrometeoroids. It is a kind of control case in planetary science, demonstrating how an icy body evolves when very little happens internally. Culturally, Umbriel is not as well known as Titania or Oberon, but it contributes to Uranus's unique system of names derived from literature. Together, the 5 major moons of Uranus reflect a blend of Shakespearean and poetic references that distinguish them from the mythologically named satellites of other planets. Umbriel's name, tied to a shadowy and melancholic figure, happens to align unusually well with its dark surface. Despite being less visually striking than Miranda with its fractured terrain, or Titania with its massive fault systems, Umbriel has its own mysteries. Why is it so dark? How did the bright Wunda ring form? And what does it tell us about the moon's interior or recent impacts? And is Umbriel's surface hiding evidence of more complex chemistry than we expect? These are the kinds of questions that future missions to Uranus could help resolve. For now, Umbriel remains a quiet, enigmatic world. It is not the most active, not the largest, not the brightest, but it may hold keys to understanding how different processes shape the moons of the outer solar system. Its dark face is like a canvas, painted by billions of years of space weathering, waiting for closer exploration to reveal what lies beneath. Titania is the largest moon of Uranus, with a diameter of about 1,578 kilometers, 981 miles, making it slightly larger than Oberon. Despite its size, Titania is still smaller than several other moons in the solar system, including Earth's moon, Ganymede, Callisto, and Titan. It was discovered in 1787 by William Herschel, the same year he identified Oberon. Herschel named it Titania after the Queen of the Fairies in Shakespeare's A Midsummer Night's Dream, and in many ways it lives up to that title as the regal centerpiece of Uranus's moon system. Titania orbits Uranus at a distance of about 436,000 kilometers, 271,000 miles, completing one revolution around the planet in roughly 8.7 Earth days. Like the other large moons of Uranus, Titania is tidally locked, meaning the same hemisphere always faces Uranus. This synchronous rotation is common among major satellites in the solar system, from our own moon to the Galilean moons of Jupiter. The surface of Titania reveals a fascinating blend of ancient and relatively younger terrain. It is moderately cratered, but not as heavily as Oberon or Umbriel, suggesting that resurfacing events erased or softened some of the older impact scars. Voyager 2's 1986 flyby provided the best images we have of Titania, covering about 40% of its surface. These images revealed massive canyons and fault valleys, some stretching for hundreds of kilometers. The largest of these is Messina Casmata, a huge valley system extending about 1,500 kilometers, 930 miles, across the moon. Features like this indicate that Titania underwent tectonic activity, likely caused by the expansion of its interior as it cooled and partially froze. The stretching of the crust would have fractured the surface, leaving behind enormous fault lines. One of the most notable craters on Titania is Gertrude, a massive impact basin about 326 kilometers, 203 miles, in diameter. Gertrude has a central dome-like uplift, which formed as the crust rebounded after the impact. Surrounding the basin are ridges and grooves that mark the force of the collision. Gertrude, combined with the tectonic valleys, illustrates Titania's dual nature. It is both an ancient world scarred by impacts and a geologically active one that reshaped itself at some point in its history. Titania's surface color is slightly redder than that of Ariel or Miranda, but not as dark as Umbriel. This reddish hue is probably due to radiation darkening and the accumulation of organic compounds on the icy surface. Spectroscopic studies from Earth and space-based telescopes suggest that Titania's crust is composed primarily of water ice, mixed with carbon dioxide and possibly ammonia hydrates. The presence of carbon dioxide is especially interesting, as it may indicate ongoing geological processes. On Titania, carbon dioxide ice is unstable over long time scales and would gradually escape into space. Its detection suggests that some mechanism, perhaps internal outgassing or chemical reactions, continues to replenish it. The interior of Titania is believed to be made of roughly equal parts rock and ice. with a density of 1.71 grams per cubic centimeter. This composition implies a differentiated structure with a rocky core surrounded by an icy mantle. Some models suggest Titania could harbor a subsurface ocean beneath its crust, perhaps kept liquid by residual heat and the presence of salts or ammonia, which lowers the freezing point of water. If true, Titania would join the growing list of icy worlds in the outer solar system, where liquid water may still exist, worlds that are scientifically fascinating because of their potential to harbor conditions favorable for life. Titania experiences extreme seasons due to Uranus's tilted rotation. For decades at a time, one of its poles receives continuous sunlight while the other sits in darkness. During Voyager 2's flyby in 1986, the southern hemisphere of Titania was in full sunlight, while the northern hemisphere remained in winter darkness. As Uranus moves along its orbit, these roles will eventually reverse. This means that the moon's poles undergo dramatic temperature cycles, which could influence the behavior of volatile ices like carbon dioxide on its surface. From a scientific perspective, Titania represents a middle ground among Uranus's moons. It is larger and more geologically active than Umbriel or Oberon, but less extreme than Ariel or Miranda in terms of tectonic or surface variety. As such, it provides important clues about how size, composition, and internal heat influence the development of icy satellites. The possibility of a subsurface ocean, combined with its tectonic activity, makes Titania one of the most compelling targets for future exploration. Culturally, Titania has an enduring resonance due to its name. As the fairy queen in Shakespeare's play, Titania embodies mystery, power, and beauty, traits that mirror the moon's role as Uranus's most prominent satellite. The naming tradition of Uranian moons helps make Titania more relatable, reminding us that human imagination and literature are interwoven with the exploration of the cosmos. Future missions to Uranus could unlock Titania's secrets. High-resolution mapping could reveal whether cryovolcanism, eruptions of water, or ammonia instead of molten rock has occurred. Spectral instruments could confirm the presence of carbon dioxide and ammonia and search for evidence of more complex chemistry. Radar sounding might even detect a buried ocean. With its size, complexity, and scientific importance, Titania stands as a prime candidate for study in the next great mission to the outer solar system. For now, Titania remains half known, its northern hemisphere unseen in detail, its interior a mystery, and its history only partially told. What we do know is enough to establish it as a world worth returning to, one that may hold answers not just about Uranus's system, but about the processes shaping icy moons across the solar system. Among all the moons of Uranus, Miranda is arguably the most surprising. At only about 471 kilometers, 293 miles in diameter, it is the smallest of the 5 major Uranian satellites, yet its surface is one of the most bizarre landscapes in the entire solar system. Miranda looks like it has been broken apart and reassembled, leaving behind gigantic cliffs, enormous canyons, and patchwork regions unlike anything else we have observed. When Voyager 2 flew by Uranus in 1986, the images it returned of Miranda stunned planetary scientists. Instead of a dull, cratered world as many had expected, Miranda revealed itself as a geological puzzle box, a place where forces both ancient and violent had left scars on a tiny body that should not have been capable of such drama. Miranda's most famous features are the so-called coronae, which are vast, oval-shaped regions of ridges, grooves, and scarps. 3 major coronae have been identified: Arden, Elsinore, and Inverness. Each of these spans hundreds of kilometers, covering significant portions of the Moon's surface. They are unlike any features seen elsewhere in the solar system. Some scientists believe the coronae formed from tectonic and cryovolcanic processes, where upwelling of partially molten ice deformed the crust. Others have suggested that Miranda may have been shattered by a colossal impact in its past and then reassembled under gravity, leaving behind the strange mismatched terrains we see today. Perhaps the most breathtaking feature on Miranda is Verona Rupes, a massive cliff that plunges 20 kilometers, 12 miles, downwards. This is the tallest known cliff in the solar system. If you were to stand at the top and step off, it would take you about 10 minutes to fall to the bottom, assuming you didn't hit anything on the way down. Features like Verona Rupes highlight just how extreme Miranda's terrain is, especially given its small size. The surface of Miranda is a mixture of ancient, cratered regions and younger, deformed areas. This contrast suggests that the Moon experienced episodes of geological activity in the past. Despite its small size, Miranda appears to have been internally active at some point, likely powered by tidal heating. Because Miranda orbits relatively close to Uranus, gravitational interactions between the Moon, Uranus, and other nearby satellites may have created orbital resonances that flexed and heated Miranda's interior. This heating could have been enough to drive partial melting of ice and trigger tectonic and cryovolcanic reshaping of the crust. Voyager 2's images revealed that Miranda's surface is brighter than Umbriel's or Oberon's, reflecting about 32% of the sunlight it receives. Its composition appears to be dominated by water ice, with some darker material mixed in. Given its small size, Miranda is unlikely to have maintained any internal liquid water in the present day. However, in the past, short-lived heating episodes could have allowed for limited geological activity, leaving behind the corona and cliffs. Miranda's orbit around Uranus is about 129,000 kilometers, 80,000 miles, making it the innermost of the 5 large moons. Like the others, it is tidally locked, always showing the same face to Uranus. Its small size and close orbit mean that it lies deep within Uranus's magnetosphere, where charged particles bombard its surface. Over time, this radiation may have contributed to the darker coloration of some of Miranda's surface patches. The origin of Miranda's strange geology remains a matter of debate. One theory suggests that the corona formed through convection in the ice mantle, with rising plumes of warmer material deforming the crust from below. Another theory argues that Miranda was once broken apart by a massive collision and later reassembled, with the coronae representing scars from this reconstruction. A third idea involves orbital resonances with other moons, which could have created repeated episodes of tidal heating and crustal disruption. Each of these possibilities highlights just how unusual Miranda is, because no other small, icy moon in the solar system shows such a combination of gigantic structures and patchwork terrain. Culturally, Miranda continues Uranus's tradition of literary names. Herschel's son, John, who suggested the naming scheme for Uranus's moons, drew Miranda from Shakespeare's play The Tempest. In the play, Miranda is a young woman who marvels at the world with wonder, exclaiming, "Oh, brave new world!" The choice of name feels fitting, as Miranda truly revealed a brave new world when Voyager 2 showed us its fractured face for the first time. For planetary scientists, Miranda is a reminder that size does not dictate complexity. Even a small moon can display geological activity and produce landscapes more extreme than those on much larger worlds. Miranda also emphasizes the role of tidal forces in shaping planetary systems. Without the gravitational interplay of Uranus and its moons, Miranda might have remained an inert icy rock. Instead, it became one of the most unique objects in the solar system. Today, Miranda stands as one of the most compelling reasons to send another mission to Uranus. A spacecraft equipped with high-resolution cameras and spectrometers could unravel how the corona formed, measure the composition of surface materials, and test theories about past tidal heating. For now, we only have a partial glimpse, and large regions of Miranda's surface remain unobserved. What Voyager 2 revealed was just enough to whet our curiosity. Miranda shows us that even the smallest moons can hold the biggest surprises. Its patchwork of terrains, its soaring cliffs, and its mysterious coronae ensure that any future journey to Uranus will put this fractured moon at the top of the list of worlds to study. Beyond the 5 large classical moons, Miranda, Ariel, Umbriel, Titania, and Oberon, Uranus possesses a collection of smaller satellites that together make its moon system one of the most diverse in the solar system. As of now, astronomers have confirmed 27 moons orbiting Uranus. And while the Big Five dominate in size and attention, the smaller bodies are just as important for understanding how this planetary system formed and evolved. The inner small moons of Uranus are found orbiting between the planet and Miranda. They are typically only a few tens of kilometers across, irregularly shaped, and often closely associated with Uranus's faint ring system. Among these are Cordelia and Ophelia, which act as shepherd moons for Uranus's Epsilon ring, the brightest and densest of its rings. Their gravitational influence helps confine the particles in the ring, preventing them from spreading out and dispersing. These moons are small, with diameters of about 40 kilometers, 25 miles or less. But they play an outsized role in maintaining the structure of the rings. Other inner moons, such as Bianca, Cressida, Desdemona, Juliet, and Portia, orbit within a relatively narrow region between 59,000 and 77,000 kilometers, 37,000 and 48,000 miles from Uranus's center. This crowded zone contains at least a dozen moons, many of which are on unstable orbits that could lead to collisions over long timescales. Some computer simulations suggest that this system of inner moons is dynamically fragile, with orbits shifting gradually due to gravitational interactions. Over millions of years, some of these moons may collide, break apart, or merge, reshaping the inner system of Uranus. The outer small moons of Uranus, by contrast, are much farther away and are thought to be captured objects from the Kuiper Belt or beyond. These include moons such as Sycorax, Caliban, and Stephano. These outer satellites orbit Uranus at distances up to several million kilometers and follow eccentric, highly inclined, and even retrograde paths. Their irregular orbits suggest that they did not form alongside Uranus, but were instead gravitationally captured after the planet formed. Studying these moons can provide clues about the environment of the early solar system and the processes that allowed Uranus to acquire companions from beyond its immediate neighborhood. Many of the small moons of Uranus remain poorly understood because they are so faint and distant. Voyager 2 imaged some of the inner moons during its flyby in 1986, but most of what we know about the outer irregular satellites comes from ground-based telescopes and later observations with the Hubble Space Telescope. Even then, details are limited. Most of these moons are little more than moving points of light against the background stars. Their sizes, shapes, and compositions remain uncertain, though their faintness suggests they are small and dark, likely made of water ice mixed with darker carbon-rich material. The naming of Uranus's moons follows the same literary theme established for the large satellites. Most are named after characters from Shakespeare's plays or from Alexander Pope's The Rape of the Lock. This tradition gives Uranus's moons a cultural distinction, while the moons of other planets draw mainly from Greek and Roman mythology. Uranus's system is tied to English literature. Names like Puck, Prospero, and Sycorax not only reflect this, but also help keep the moons memorable, even if they are scientifically obscure. The small moons highlight the range of processes at work in planetary systems. The inner shepherd moons directly influence Uranus's rings. The crowded middle moons show how gravitational interactions can destabilize orbits over time. The outer irregular moons demonstrate how giant planets can capture objects from farther out in the solar system. Each group tells a different story, but together they show that Uranus's system is not static. It is dynamic, evolving, and in some ways precarious. The study of these smaller moons is important for planetary science because they provide natural laboratories for understanding orbital dynamics, planetary rings, and the history of captures in the outer solar system. Future missions to Uranus would be able to explore them up close, imaging their surfaces, measuring their densities, and unraveling their relationships to the rings and the planet itself. For now, however, they remain distant, faint, and mysterious. In the grand scheme of Uranus's system, the small moons may seem like background players compared to Titania, Oberon, or Miranda. But their roles are significant, shaping the rings, providing insight into gravitational chaos, and reminding us that even tiny worlds can hold important clues about the history of the solar system. In January 1986, humanity got its only close-up look at Uranus when NASA's Voyager 2 spacecraft swept past the planet on its long journey through the outer solar system. Launched in 1977, Voyager 2 had already delivered groundbreaking discoveries at Jupiter in 1979 and Saturn in 1981. Its trajectory was carefully chosen to take advantage of a rare planetary alignment, allowing it to slingshot from one giant planet to the next using their gravity. By the time it reached Uranus, Voyager 2 was nearly a decade into its mission, more than 2.8 billion kilometers, 1.7 billion miles from Earth, and ready to open a new chapter in planetary exploration. Voyager 2's closest approach to Uranus occurred on January 24, 1986, when it passed within about 81,500 kilometers, 50,600 miles, of the planet's cloud tops. During the flyby, the spacecraft collected data using its suite of instruments, including cameras, spectrometers, magnetometers, and particle detectors. This was the first and remains the only at this time a spacecraft has visited Uranus up close. The observations transformed Uranus from a fuzzy bluish dot in telescopes into a real world with rings, moons, and atmospheric dynamics. One of Voyager 2's first major contributions was the discovery of 10 new moons, many of which were small and located near Uranus's rings. These discoveries expanded the known family of Uranian satellites beyond the 5 classical moons and provided the first images of the planet's faint inner system. The spacecraft also imaged the large moons in far greater detail than had ever been possible from Earth, revealing diverse surfaces that ranged from the heavily cratered Umbriel and Oberon to the fractured chaotic terrain of Miranda. Voyager 2 also confirmed the existence of Uranus's ring system, first detected from Earth in 1977, and provided detailed images of it. The spacecraft revealed that Uranus has 11 distinct rings, most of them narrow and dark, composed of small, dark particles. The faintness and narrowness of the rings made them very different from Saturn's bright, broad rings, suggesting a unique history and structure. The presence of nearby shepherd moons, such as Cordelia and Ophelia, was also confirmed, showing how small moons help keep the rings confined. Perhaps one of the most surprising findings came from the study of Uranus's magnetic field. Voyager 2 detected that the field is tilted about 59 degrees from the planet's rotational axis and is offset from the planet's center by nearly 1/3 of its radius. This unusual geometry means that Uranus's magnetosphere is lopsided and asymmetric, sweeping around in unpredictable ways as the planet rotates on its side. This was the first time scientists had encountered such a peculiar magnetic configuration, and it remains one of the enduring mysteries of Uranus. Voyager 2 also measured Uranus's atmosphere. It found that the planet is made mostly of hydrogen and helium, with methane giving Uranus its pale blue-green color by absorbing red light. Unlike Jupiter or Saturn, Uranus showed very few visible cloud features in Voyager 2's images. The planet appeared bland, with a uniform hazy atmosphere. This led to the initial impression that Uranus was the boring giant planet. However, later observations from the Hubble Space Telescope and ground-based observatories revealed that Uranus can produce storms and dynamic weather, which Voyager 2's quick flyby may have missed due to timing. The spacecraft also measured Uranus's temperature and energy balance, confirming that it is the coldest planet in the solar system, with a minimum atmospheric temperature of around minus 224 degrees Celsius, minus 371 degrees Fahrenheit. This was especially surprising given that Neptune, farther from the Sun, appears to emit more internal heat than Uranus. Why Uranus has such a low internal heat output remains a mystery and is one of the key questions scientists hope to answer with future missions. The flyby was not without its limitations. Because Voyager 2 had to continue on to Neptune, the encounter was brief, lasting only a matter of hours at closest approach. The spacecraft could only study one hemisphere of Uranus's moons and rings in detail, leaving the other half unseen. Additionally, the low lighting conditions during Uranus's southern summer meant that large regions of the planet's atmosphere were in shadow, limiting what could be observed. Despite these constraints, the Voyager 2 encounter was a triumph of planetary exploration. It expanded our knowledge of Uranus enormously and gave humanity its only close-up images of the planet and its moons to date. The data gathered by the spacecraft continued to be analyzed decades later, offering insights into Uranus's composition, magnetic field, and satellite system. Voyager 2's journey did not end at Uranus. After its flyby, the spacecraft continued on to Neptune, where in 1989 it provided another historic encounter. Today, Voyager 2 is still operational, transmitting data back to Earth from the far reaches of interstellar space. Its visit to Uranus remains a reminder of what a single spacecraft, launched in an era before modern computers or digital imaging, could achieve. For Uranus itself, Voyager 2's flyby was a beginning rather than an end. It raised more questions than it answered. Why is Uranus tilted so dramatically? Why is its magnetic field so unusual? What drives its faint ring system? What lies beneath the surfaces of its moons? These questions remain open, and they form the basis of the scientific case for returning to Uranus with a dedicated mission. The Voyager 2 flyby of Uranus in 1986 was a watershed moment in planetary science. Before the spacecraft's arrival, Uranus was little more than a faint bluish point of light in telescopes. Astronomers knew it was a gas giant, had a few large moons, and possessed a faint ring system discovered in 1977. But the details of its nature were largely speculation. Voyager 2 changed that. In just a few days of close observation, the spacecraft turned Uranus from an abstraction into a real world. Its discoveries, while limited in scope by the quick flyby, reshaped our understanding of this unusual planet and its system of moons and rings. One of the most significant revelations was the confirmation and characterization of Uranus's ring system. Earth-based observations had hinted at the presence of rings when a star's light flickered as Uranus passed in front of it, but Voyager 2 showed these were real narrow bands encircling the planet. The spacecraft identified 11 distinct rings, most of them dark and composed of small, charcoal-colored particles. Unlike Saturn's bright icy rings, Uranus's are faint and difficult to detect, suggesting differences in composition, age, and maintenance. Voyager 2 also captured images of the small shepherd moons Cordelia and Ophelia, whose gravitational influence combines Uranus's outermost epsilon ring. This discovery reinforced the idea that moons and rings are interconnected systems, with small bodies playing critical roles in shaping planetary environments. The spacecraft also provided the first close-up views of Uranus's 5 major moons: Miranda, Ariel, Umbriel, Titania, and Oberon. Each revealed unique characteristics. Miranda's chaotic terrain with giant cliffs and strange corona shocked scientists, showing that even a small moon can be geologically complex. Ariel displayed valleys and fault lines, evidence of tectonic activity. Titania and Oberon revealed a balance of cratering and resurfacing, while Umbriel stood out as the darkest of the 5, suggesting a surface weathered by radiation or coated in dark material. These images established Uranus's moons as worlds in their own right, worthy of exploration and comparison to the moons of Jupiter and Saturn. Voyager 2 also measured Uranus's magnetic field, which turned out to be far stranger than expected. Instead of being aligned with the planet's rotation axis and centered, as on Earth and Jupiter, Uranus's magnetic field is tilted by nearly 60 degrees and offset from the planet's core by almost 1/3 of its radius. This creates a magnetosphere that is lopsided and dynamic, flipping and sweeping as Uranus rotates. The finding forced scientists to rethink models of how planetary magnetic fields can form and behave. It also raised questions about the planet's internal structure, since the unusual field might reflect differences in how electrical currents move in Uranus's interior layers compared to other planets. Another important contribution came from Voyager 2's atmospheric observations. Using its instruments, the spacecraft confirmed that Uranus's atmosphere is dominated by hydrogen and helium, with about 2% methane. The methane is critical because it absorbs red light, giving Uranus its pale blue-green color. Surprisingly, the atmosphere appeared featureless in visible light, with no large cloud belts, storms, or vortices like those seen on Jupiter or Saturn. This bland appearance initially gave Uranus a reputation as the boring giant planet. Yet infrared measurements revealed subtle temperature variations and faint cloud structures that hinted at underlying dynamics. Later observations from Earth would show that Uranus can in fact generate storms and weather, but Voyager 2 captured it during a relatively calm period. Temperature measurements revealed another mystery. Uranus is the coldest planet in the solar system, with atmospheric temperatures plunging to around minus 224 degrees Celsius, minus 371 degrees Fahrenheit. This is colder than Neptune, which lies farther from the Sun. Voyager 2's instruments showed that Uranus radiates very little internal heat, unlike Jupiter, Saturn, and Neptune, which emit more energy than they receive from the Sun. The reason for Uranus's low heat output remains an unresolved puzzle. Some scientists propose that a past catastrophic event, like the giant impact that tipped Uranus onto its head, could have disrupted its interior, preventing heat from escaping in the way it does on other planets. Voyager 2 also measured Uranus's rotation more precisely, determining that the planet spins once every 17.24 hours. Combined with its extreme axial tilt of 98 degrees, this means Uranus experiences seasons unlike any other planet. At the time of Voyager 2's encounter, the planet's southern hemisphere was in the middle of a decades-long summer, with one pole pointed almost directly at the sun. This unusual geometry influenced what the spacecraft could observe, since much of the northern hemisphere was cloaked in darkness. Perhaps just as significant as the discoveries themselves were the questions Voyager 2 left behind. Why is Uranus tilted so dramatically? What causes its strange magnetic field? How active are its moons geologically? And do any of them harbor subsurface oceans? Why is Uranus so much colder than expected? The flyby showed us just enough to recognize how unusual Uranus is, but not enough to explain its mysteries. From a broader perspective, Voyager 2's visit established Uranus as a planetary system worth returning to. The spacecraft revealed a complex world of rings, moons, and magnetic oddities that defy easy classification. It also highlighted the limitations of a single, quick flyby. To truly understand Uranus, scientists realized we would need an orbiter capable of studying it over months or years, monitoring its weather, mapping its moons, and probing its magnetic field. In the decades since Voyager 2's flyby, astronomers have continued to study Uranus with telescopes like Hubble and ground-based observatories, filling in some of the gaps. But no spacecraft has returned, and much of Uranus remains unexplored. What Voyager 2 accomplished was remarkable. In just a few days, it transformed Uranus from a distant dot into a real dynamic system, rich with questions. Its flyby remains one of the great achievements of space exploration and a reminder of how much we still have left to learn. When Voyager 2 sped past Uranus in January 1986, it left behind a tantalizing glimpse of a planet system filled with mysteries, but gave us only a fraction of the story. Since no other spacecraft has visited Uranus since then, astronomers have had to rely on Earth-based telescopes and orbiting observatories like the Hubble Space Telescope to continue unraveling the planet's secrets. Although these tools cannot match the resolution of a spacecraft flyby, they have provided decades of steady observations that revealed Uranus to be far more dynamic and complex than the featureless world Voyager 2 appeared to show. One of the most significant contributions has come from tracking Uranus's atmosphere. Voyager 2's images made the planet look bland, with few visible clouds or storms. This impression was partly due to timing. The flyby occurred during Uranus's southern summer solstice, when the planet's southern hemisphere was fully illuminated and atmospheric activity may have been minimal. Later, in the 1990s and 2000s, as Uranus moved toward its equinox, telescopes detected far more weather activity. Ground-based observatories, using adaptive optics and Hubble's ultraviolet and near-infrared instruments, revealed cloud bands, bright spots, and massive storms. In 2006, for example, astronomers observed a storm nearly the size of North America, raging in Uranus's northern hemisphere. This demonstrated that Uranus is not the quiet, static world it first appeared to be, but rather one capable of surprising bursts of activity. The Hubble Space Telescope has also monitored Uranus's unusual auroras. Auroras occur when charged particles from the solar wind interact with a planet's magnetic field and atmosphere. On Earth, they create shimmering curtains of light near the poles. Uranus's auroras, first detected in 2011, are different. Because the magnetic field is tilted nearly 60 degrees from the planet's rotation axis and offset from its center, the auroras appear in unexpected locations, sometimes far from the poles. These observations provided new clues about how Uranus's magnetosphere interacts with the solar wind, which is critical for understanding the unusual shape and dynamics of the field that Voyager 2 first measured. Ground-based and space-based observations have also expanded our understanding of Uranus's rings. Voyager 2 confirmed the existence of 11 rings, but more powerful telescopes later revealed additional faint rings beyond those detected in 1986. Hubble's sensitive instruments detected 2 outer rings, including one located about twice as far from Uranus as the previously known system. Interestingly, the outermost of these rings is blue in color, likely due to the presence of small, fine ice particles that scatter blue light more efficiently. The discovery of these outer rings demonstrated that Uranus's ring system is more extensive and complex than Voyager 2 showed. The moons of Uranus have also been revisited from afar. Although telescopic observations cannot match the detail of Voyager 2's images, long-term monitoring has allowed astronomers to refine the orbits of the small inner moons, some of which appear to be on unstable paths. Computer simulations based on these observations suggest that collisions or mergers between Uranus's small moons may occur on timescales of millions of years. This highlights the fragile and evolving nature of the planet's inner system, where gravitational tugs and nudges can gradually destabilize orbits. Hubble and other observatories have also confirmed the presence of carbon dioxide ice on the surfaces of some of Uranus's moons, particularly Ariel and Titania. This is intriguing because carbon dioxide ice is unstable over long time scales at Uranus's distance from the Sun. Its persistence suggests active replenishment, perhaps through geological processes or chemical reactions on the Moon's surfaces. These observations hint that Uranus's moons may not be completely inert, and that some of them could still harbor interesting internal activity or chemical complexity. Seasonal changes have been another key focus of post-Voyager observations. With Uranus tilted on its side, each hemisphere experiences decades-long stretches of continuous sunlight or darkness. As the planet orbits the Sun every 84 years, these extreme seasons unfold slowly. In 2007, Uranus reached its equinox when the Sun shone directly on its equator and both hemispheres received equal light. Astronomers used this rare opportunity to observe how the planet's atmosphere responded to the shift. The increase in storm activity around that time suggested that Uranus's weather is strongly tied to its extreme seasonal cycle. Monitoring these changes over decades has given scientists a longer-term perspective that a quick flyby could never provide. More recently, the use of powerful ground-based telescopes such as Keck in Hawaii and the Very Large Telescope in Chile has allowed astronomers to capture sharper images of Uranus and its moons using adaptive optics, which correct for Earth's atmospheric distortions. These facilities, combined with space observatories, have provided a more complete view of Uranus's evolving atmosphere, its ring system, and its dynamic moons. Together, the decades of observations since Voyager 2 have revealed Uranus to be anything but static. Its atmosphere is capable of producing giant storms and evolving cloud features. Its rings extend farther and are more varied than first thought. Its magnetosphere produces unusual auroras tied to its tilted field. Its moons may still be undergoing subtle geological or chemical processes. Each new discovery reinforces the idea that Uranus is a dynamic system, deserving of closer study by a dedicated mission. At the same time, these observations also emphasize the limitations of telescopes. Even the best Earth-based or space-based instruments cannot replace the detailed, high-resolution measurements that only a spacecraft can provide. Much of Uranus's northern hemisphere, unseen by Voyager 2, remains poorly understood. The surfaces of many of its smaller moons are still invisible to us. The interior structure of Uranus, hinted at by its strange magnetic field and low heat emission, remains almost entirely a mystery. For now, the work of Hubble, Keck, and other observatories has kept Uranus in the scientific spotlight and revealed it to be far more complex than once imagined. But the next major breakthroughs will likely require going back with new spacecraft, a prospect that grows more compelling with each passing year. While visible light images capture the most familiar views of Uranus, much of the planet's true character is revealed only when scientists look beyond the human eye. Infrared and radio observations, in particular, have been essential for uncovering details about the planet's atmosphere, rings, magnetosphere, and thermal properties. These methods allow astronomers to study Uranus in wavelengths that pass through clouds, reveal hidden heat patterns, and detect signals invisible in ordinary light. Infrared observations have been especially valuable for probing Uranus's atmosphere. Voyager 2 in 1986 found that Uranus emitted very little internal heat compared to other giant planets. This was a puzzle, since Jupiter, Saturn, and Neptune all radiate more heat than they receive from the Sun. To follow up, astronomers turned to ground-based infrared telescopes and later to space observatories like the Infrared Space Observatory and the Spitzer Space Telescope. These instruments confirm that Uranus's effective temperature is only about 59 Kelvin, or minus 214 degrees Celsius, minus 353 degrees Fahrenheit, just slightly warmer than what would be expected if it had no internal heat source at all. This makes Uranus the coldest planet in the solar system, colder even than Neptune despite being closer to the Sun. Infrared imaging has also revealed atmospheric dynamics that Voyager 2's cameras could not see. In near-infrared wavelengths, astronomers observed high-altitude methane clouds and discrete storm systems. Infrared data helped track how these features evolved with time, particularly around the 2007 equinox, when Uranus's equator faced the Sun. Observations showed dramatic changes in cloud patterns, suggesting that the planet's weather is strongly influenced by its extreme seasonal cycle. Infrared spectroscopy has also provided detailed measurements of atmospheric composition, confirming high levels of methane and detecting trace amounts of other gases like ethane, acetylene, and carbon monoxide. These minor species, although present in tiny amounts, are important for understanding photochemistry in Uranus's upper atmosphere. Another critical use of infrared has been in studying Uranus's rings. Unlike Saturn's bright and icy rings, Uranus's rings are dark and difficult to detect in visible light. Infrared observations from the Keck Observatory and the Hubble Space Telescope helped reveal their structure more clearly. They showed that the rings are composed of material with varying particle sizes, from large boulders to fine dust. Infrared data also indicated that some of the rings contain surprisingly bright material, possibly fresh ice exposed by recent impacts or collisions. These findings suggest that the rings are not entirely static, but are being replenished or modified over time. Radio observations have added another dimension to Uranus research. When Voyager 2 passed by the planet, its instruments detected intense radio emissions associated with Uranus's magnetosphere. These emissions, similar to those produced by Earth's auroras, are generated by charged particles spiraling along magnetic field lines. The discovery confirmed that Uranus has a magnetic field unlike any other in the solar system, with a 59-degree tilt and a significant offset from the planet's center. Since then, radio telescopes on Earth have monitored Uranus to study how its magnetosphere responds to solar wind conditions. These measurements help scientists model the planet's magnetic interactions and predict auroral activity, even without direct imaging. Radio techniques have also been used to probe Uranus's atmosphere through occultations. When Uranus passes in front of a background radio source, like a distant quasar or spacecraft signal, the planet's atmosphere bends and absorbs the radio waves. By analyzing how the signal changes, astronomers can derive information about atmospheric density, pressure, and temperature at different altitudes. These studies have confirmed the presence of a layered atmosphere with distinct regions where methane and other gases play dominant roles. Another important contribution has come from sub-millimeter and microwave observations. These wavelengths, sitting between infrared and radio, provide insights into Uranus's deep atmosphere and thermal structure. Observations with instruments like the Atacama Large Millimeter / Sub-Millimeter Array ALMA have revealed temperature variations, wind patterns, and the distribution of trace gases. These measurements help fill the gaps left by infrared and radio studies, offering a more complete picture of how Uranus's atmosphere circulates and evolves. Infrared and radio data have also extended to Uranus's moons. For example, Spectroscopy of Ariel, Tadnia, and Oberon detected water ice as the dominant surface material, with signatures of carbon dioxide ice as well. The distribution of these ices varies from moon to moon, raising questions about their geological histories and possible ongoing surface processes. Radio occultation studies during Voyager 2's flyby also hinted at tenuous atmospheres around some moons, though follow-up observations have not confirmed persistent atmospheres. Taken together, infrared and radio observations have transformed Uranus from an apparently bland, cold planet into a world with complex atmospheric chemistry, surprising weather, dynamic rings, and a magnetosphere unlike any other. These techniques continue to be vital today, since no spacecraft has returned for a closer look. Each new study adds a layer of detail that helps scientists prepare for the next mission and refine the big questions we still have. Infrared and radio astronomy remind us that even when we cannot send spacecraft, the universe offers many different ways to listen and see. By capturing signals invisible to human eyes, these methods let us uncover patterns that redefine our understanding of Uranus and the outer solar system as a whole. Uranus and Neptune are often grouped together as the ice giants, a category distinct from the larger gas giants Jupiter and Saturn. At first glance, the two planets appear to share many similarities. They are close in size, both around 4 times Earth's diameter. They have comparable masses, with Neptune being only about 17% more massive than Uranus. They orbit in the distant reaches of the solar system, well beyond the asteroid belt and Jupiter's gravitational dominance. Their bluish-green colors, caused by methane in their atmospheres absorbing red light, give them a nearly twin-like appearance in telescopic images. Yet, beneath these surface-level similarities, Uranus and Neptune reveal striking differences that make each planet unique. One of the most obvious contrasts lies in their internal heat. As noted earlier, Uranus radiates very little heat beyond what it receives from the Sun, making it the coldest planet in the solar system. Neptune, on the other hand, emits about 2.6 times the heat it absorbs. This discrepancy is puzzling because the two planets likely formed under similar conditions and contained similar proportions of hydrogen, helium, and heavier elements. One explanation suggests that Uranus may have experienced a massive collision early in its history that disrupted its interior, possibly trapping heat in layers where it cannot escape. Neptune, by contrast, might have retained a more efficient mechanism for transporting heat from its core to the atmosphere, fueling its dynamic weather. This difference in heat output helps explain the contrasting weather patterns observed on the two planets. Neptune is known for its violent storms, including the Great Dark Spot, observed by Voyager 2 in 1989, which rivaled Jupiter's Great Red Spot in size. High-speed winds reaching up to 2,100 kilometers per hour, about 1,300 miles per hour, whip around Neptune's atmosphere, making it the windiest planet in the solar system. Uranus, by contrast, appeared almost featureless during Voyager 2's flyby in 1986, with only faint cloud structures visible. Later, telescopic observations have revealed that Uranus does have storms, sometimes large ones, but they are far less frequent and less intense than Neptune's. This difference likely stems from Neptune's stronger internal heat driving more vigorous convection in its atmosphere. Magnetic fields provide another point of contrast. Both Uranus and Neptune have magnetic fields that are highly tilted relative to their rotation axes and offset from their planetary centers. For Uranus, the tilt is about 59 degrees, while Neptune's is around 47 degrees. This means both planets have magnetospheres that wobble dramatically as the planets rotate, unlike the more aligned fields of Earth, Jupiter, and Saturn. The similarities suggest a common mechanism behind their magnetic generation, possibly involving a conductive slush of water, ammonia, and methane in the planet's mantles. However, Uranus's extreme tilt, combined with its rotation axis being tipped almost on its side, makes its magnetosphere even stranger than Neptune's, producing auroras and interactions with the solar wind that defy expectations. Their ring systems also differ in subtle but important ways. Uranus's rings are narrow, dark, and composed mostly of large rocky particles. Neptune's rings are faint, dusty, and incomplete, with bright clumps known as arcs that remain puzzling even today. These arcs appear to be stabilized by the gravitational influence of nearby moons, preventing them from dispersing around the entire ring. Uranus's rings, while not as bright or extensive as Saturn's, are more sharply defined, with some appearing only a few kilometers wide. The differences highlight the varied processes shaping ring systems, even among planets with similar environments. The moons of Uranus and Neptune also reveal contrasts. Uranus has a larger collection of medium-sized moons, including Miranda, Ariel, Umbriel, and Oberon, each with unique surface features shaped by past geological activity. Neptune's primary moon, Triton, dominates its system. Triton is nearly as large as Pluto and is unique in orbiting Neptune in a retrograde direction, meaning it moves opposite to Neptune's rotation. This strongly suggests that Triton was captured from the Kuiper Belt rather than forming alongside Neptune. Triton is also geologically active today, with nitrogen geysers and a surface shaped by cryovolcanism, making it one of the most fascinating worlds in the solar system. Uranus's moons, by contrast, show signs of ancient activity but are not known to be active in the present day. From an orbital perspective, Neptune lies slightly farther from the Sun at about 30 astronomical units compared to Uranus at 19 AU. This extra distance results in a colder environment overall. Yet, paradoxically, Neptune is warmer internally. The two planets' positions also play a role in shaping the outer solar system. Neptune, in particular, has been influential in sculpting the Kuiper Belt, with its gravity creating resonant orbits like that of Pluto. Uranus, closer in, exerts less influence on distant small bodies, but has its own complex interactions with its moons and rings. Comparing Uranus and Neptune helps astronomers refine their understanding of planet formation and evolution. Why did two planets with similar sizes and compositions end up with such different heat outputs and atmospheric behaviors? What can their magnetic fields tell us about the processes occurring deep inside ice giants? And how do their moons and rings illustrate the varied histories of planetary systems? These questions remain at the forefront of planetary science, making Uranus and Neptune valuable laboratories for studying worlds that fall outside the traditional categories of rocky planets and gas giants. The study of Uranus and Neptune also carries implications beyond our solar system. Many exoplanets discovered around other stars fall into a size range similar to these ice giants. Understanding the similarities and differences between Uranus and Neptune provides a framework for interpreting the properties of those distant worlds. In this sense, comparing the two planets is not just an exercise in solar system science, but a key step in broadening our perspective on planetary systems throughout the galaxy. The story of Uranus does not end with telescopes and spacecraft. It also extends into language, culture, and the way humanity has chosen to frame this distant world in myth and imagination. Unlike Mercury, Venus, Mars, Jupiter, and Saturn, Uranus was not known to ancient civilizations. Those 5 planets are bright enough to be seen with the naked eye and were woven into mythologies thousands of years before modern science. Uranus, however, required the telescope to be revealed as a planet in 1781, which meant its cultural associations had to be created in the modern era. When William Herschel discovered the planet, he originally wanted to name it Georgium Sidus, or George's Star, in honor of King George III of England. This suggestion was unsurprisingly unpopular outside of Britain. Astronomers on the European continent argued for a name consistent with the mythological tradition, where planets were named after Roman gods. After some debate, the German astronomer Johann Elert Bode proposed the name Uranus, drawing from Greek mythology rather than Roman. Uranus was the primordial sky god, the father of Saturn, Cronus in Greek, and grandfather of Jupiter, Zeus. The choice kept the generational theme: Uranus fathered Saturn, Saturn fathered Jupiter, and Jupiter in turn fathered Mars in some traditions. The name was eventually adopted internationally, though it took decades for it to gain universal acceptance. Culturally, Uranus has not had the same impact as planets like Mars or Saturn. Part of this is timing. By the late 18th and 19th centuries, when Uranus was discovered and named, society was already entering the age of scientific rationalism. The planet was not as deeply tied into ancient myth systems, and its remote location made it less prominent in literature and astrology. That said, Uranus still found a place in symbolic systems. In astrology, it became associated with sudden change, revolution, and innovation, reflecting the upheavals of the late 18th century, including the American and French revolutions. The discovery of Uranus was seen as a cosmic symbol of breaking with tradition and entering a new era. In modern culture, Uranus is often the subject of humor because of how its name is pronounced in English. This unfortunate accident of linguistics has overshadowed more serious cultural treatment in popular media. Science fiction, however, has occasionally drawn on Uranus as a setting or reference point. Mid-20th century pulp magazines sometimes depicted explorers venturing to Uranus, though usually with little scientific accuracy. More recently, Uranus appears in speculative fiction as a mysterious, icy frontier, often less explored than Mars, Jupiter, or Saturn. Its tilted axis and extreme seasons make it an evocative backdrop for storytelling, even if it is not as commonly used as its neighbors. The naming of Uranus's moons reflects another cultural connection. Unlike most planetary moons, which draw from Greco-Roman mythology, Uranus's moons are named after characters from the works of William Shakespeare and Alexander Pope. The first two moons discovered, Titania and Oberon, take their names from A Midsummer Night's Dream. Later discoveries added names such as Ariel, Umbriel, and Miranda. This literary naming scheme was proposed by John Herschel, the son of Uranus's discoverer, and it has endured ever since. The tradition sets Uranus apart in the solar system, with its satellites bearing names drawn not from gods and titans, but from plays and poems. This decision gave Uranus's moons a uniquely cultural identity, bridging the world of science with the arts. The cultural impact of Uranus also includes its role in expanding humanity's view of the solar system. Its discovery was the first time since antiquity that the known boundaries of the planetary system were extended. Before Herschel's work, Saturn was thought to be the last planet. The realization that there was another world beyond shifted the way people thought about the cosmos. It suggested that the solar system was larger and more populated than once believed, opening the door to the later discoveries of Neptune, Pluto, and countless smaller bodies. In this way, Uranus symbolizes an expansion of human knowledge and a breaking of perceived limits. Despite its relatively minor role in broader cultural narratives, Uranus remains an important symbol in the history of astronomy. Its naming reflects a careful balance between mythology and modernity, between honoring tradition and embracing discovery. Its moons highlight the blending of science and literature, and its very discovery represents a turning point where humanity began to realize that the solar system was not a closed, easily mapped system, but an open frontier waiting to be explored. Even after more than 2 centuries of telescopic study and the one brief flyby by Voyager 2, Uranus continues to puzzle astronomers. In some respects, we know less about Uranus than we do about Mars, Jupiter, or even some moons of Saturn. This is not because Uranus is less interesting, but because it has been largely neglected in planetary exploration. As a result, many of the key questions about Uranus remain open, fueling scientific debate and speculation. One of the most enduring mysteries is Uranus's internal heat, or rather, the lack of it. Every other giant planet radiates more energy into space than it receives from the sun, a sign of lingering heat from formation or ongoing processes within their interiors. Uranus, by contrast, radiates almost nothing extra, making it the coldest planet in the solar system. Scientists debate whether this means Uranus lost its heat through some violent event, such as a massive collision early in its history, or whether its interior somehow traps heat in layers that cannot easily rise to the surface. Understanding this discrepancy is critical not only for Uranus itself, but also for understanding the broader class of ice giant planets, which are common among exoplanet discoveries. Another major puzzle is Uranus's unusual tilt. Its axis of rotation is tipped by 98 degrees, making it roll around the Sun on its side. The prevailing theory suggests that Uranus was struck by one or more large protoplanets billions of years ago, knocking it into this configuration. Yet the details remain unclear. Was it one catastrophic collision or a series of smaller impacts? How did such an event affect the planet's interior structure, its magnetosphere, and its moons? Some models suggest that the impact could have reshaped Uranus's internal layers, explaining its weak heat output and strange magnetic field. Others argue that the tilt may have evolved gradually under complex gravitational interactions. The magnetic field of Uranus is itself a deep mystery. Unlike Earth's, which is roughly aligned with the planet's rotation axis and centered on the core, Uranus's magnetic field is tilted by nearly 60 degrees and offset from the center by about 1/3 of the planet's radius. This produces a lopsided magnetosphere that behaves in ways difficult to predict. Voyager 2 revealed some of these quirks, but without long-term monitoring, many questions remain unanswered. How exactly does Uranus generate this field? What does it imply about the structure of its interior? And what unique effects does this have on the planet's interaction with the solar wind? The moons of Uranus also raise intriguing questions. Voyager 2 revealed signs of past geological activity on several of them, particularly Ariel and Miranda. Ariel shows signs of tectonic rifts and resurfacing, while Miranda has bizarre cliffs and patchwork terrain that suggest internal activity. But without further exploration, scientists cannot determine whether any of these moons are still active today or what processes shape them. There is even speculation that some of Uranus's moons might harbor subsurface oceans, like Europa or Enceladus, although evidence is lacking. If true, this would make them potential candidates for astrobiology. The rings of Uranus add another layer of uncertainty. They are dark, narrow, and composed of larger particles than Saturn's bright, icy rings. Their composition and origin remain poorly understood. Some scientists believe they are remnants of shattered moons, while others suggest they are relatively young features created by ongoing collisions. Observations have shown that the rings may not be stable over long time scales, raising questions about how they are replenished. Seasonal changes present another unresolved issue. With its extreme tilt, Uranus experiences decades-long seasons, and we have observed only part of a single cycle since its discovery. How does the atmosphere respond to these slow but dramatic shifts in sunlight? Observations around the 2007 equinox revealed increased storm activity, but the long-term patterns remain unclear. Only continued monitoring over many decades will fully reveal how Uranus's atmosphere changes with the seasons. Beyond these scientific debates, Uranus also represents a larger mystery. Why it and Neptune turned out so differently, despite their apparent similarities. Both are ice giants, with similar compositions, yet Neptune is warmer and more active, while Uranus is colder and calmer. Untangling this divergence could shed light on how planetary systems evolve and why similar starting conditions can produce very different outcomes. These unresolved questions are more than just curiosities. They point to gaps in our understanding of planetary science as a whole. With so many exoplanets resembling Uranus and Neptune in size, learning more about them is essential for interpreting the growing data on worlds beyond our solar system. Uranus remains a laboratory waiting to be explored, holding answers that could change how we think about planetary formation, evolution, and habitability. Among all the planets that remain underexplored, Uranus stands out as one of the most compelling destinations for a new spacecraft. Voyager 2's flyby in 1986 provided the only close-up images and direct measurements of Uranus and its system of moons, rings, and magnetic field. But that brief encounter lasted only a matter of hours, and it left more questions than it answered. In the decades since, every other giant planet, Jupiter, Saturn, and even Neptune to a lesser degree, has received more attention. Uranus, by contrast, has been left in the shadows, despite offering some of the most unusual features of any planet. One of the strongest scientific reasons for revisiting Uranus lies in its unique classification as an ice giant. While Jupiter and Saturn are gas giants dominated by hydrogen and helium, Uranus and Neptune contain larger fractions of heavier elements such as water, methane, and ammonia. These ices, mixed with rock and gas, give ice giants a fundamentally different structure. Exoplanet surveys have revealed that planets of similar size to Uranus and Neptune are among the most common types in the galaxy. Yet, in our own solar system, we have barely studied them. A dedicated mission to Uranus would not only expand our understanding of one planet, but also provide crucial insights into a whole category of worlds beyond our own system. The mysteries of Uranus itself make it an enticing target. The planet's sideways tilt remains unexplained. Its magnetosphere is tilted and offset in ways unlike any other known planetary field, and its atmosphere is the coldest of all the major planets. A mission could investigate whether a giant collision shaped these features or whether more subtle processes are at play. Understanding Uranus's lack of internal heat compared to Neptune would shed light on how planetary interiors evolve. These are fundamental questions about planetary physics that cannot be answered from Earth. The moons of Uranus also provide compelling reasons for exploration. Voyager 2 showed that several of them, especially Ariel, Miranda, Titania, and Oberon, display evidence of past geological activity. Ariel appears to have been resurfaced by flows of material, while Miranda has towering cliffs and patchwork terrain that suggest internal upheaval. If these moons harbor subsurface oceans, as some models propose, they could even represent potential habitats for life. A mission to Uranus could perform flybys of these moons, mapping their surfaces in detail, searching for signs of ongoing activity, and probing their interiors with instruments designed to detect liquid water beneath the ice. Uranus's ring system, though less spectacular than Saturn's, is another area ripe for exploration. Its dark, narrow rings remain poorly understood, and their composition and stability raise questions about their origin. A spacecraft equipped with cameras and spectrometers could study the rings at high resolution, observing how they interact with nearby moons and determining whether they are remnants of destroyed satellites or products of ongoing processes. Another factor in favor of a Uranus mission is timing. Planetary alignments are not always favorable, but the 2030s and 2040s present an opportunity to send a spacecraft that could reach Uranus in under 2 decades with current propulsion technology. The U.S. National Academies of Sciences, in its Decadal Survey released in 2022, specifically identified a Uranus orbiter and probe as the top priority for a flagship planetary mission. This reflects a broad consensus in the scientific community that Uranus is both scientifically rich and logistically feasible for exploration within the next generation. Such a mission would likely include 2 key components: an orbiter to study Uranus and its moons over an extended period, and an atmospheric probe to dive into the planet's atmosphere. The probe could measure temperature, pressure, winds, and composition directly, providing data impossible to obtain from telescopes. The orbiter could remain in the Uranian system for years, observing seasonal changes, monitoring storms, and conducting multiple moon flybys. This combination would give scientists a complete picture of Uranus as both a planet and a planetary system. Beyond pure science, there is also the symbolic value of returning to Uranus. Each time humanity has sent spacecraft to a new world, the results have transformed our understanding of the solar system. Think of Galileo's revelations at Jupiter, Cassini's discoveries at Saturn, or New Horizons' dramatic flyby of Pluto. Uranus is one of the last frontiers in our own planetary backyard, a place we have glimpsed but not truly explored. A mission there would continue the tradition of bold exploration that has always defined space science. In short, Uranus checks every box for a high-priority mission: scientific importance, relevance to exoplanet research, intriguing moons, unusual atmospheric and magnetic phenomena, and achievable mission design. Its exploration would not only solve long-standing mysteries, but also open new horizons in our understanding of planetary systems both near and far. For scientists and space agencies alike, Uranus represents a challenge and an opportunity too significant to ignore. Ever since Voyager 2 sped past Uranus in 1986, planetary scientists have been calling for a return. That brief encounter raised far more questions than it answered, and nearly 4. Decades later, Uranus remains one of the least explored planets in the solar system. Over the years, several mission concepts have been proposed, studied, and debated, but none have yet materialized into an actual spacecraft. Looking at this history reveals both the challenges and the growing urgency of exploring Uranus. In the late 1980s and 1990s, not long after Voyager's flyby, NASA considered follow-up missions to both Uranus and Neptune. Concepts ranged from flybys to orbiters, but enthusiasm was tempered by budgetary constraints and competing priorities. At the time, major resources were being directed toward the Galileo mission at Jupiter and the Cassini-Huygens mission to Saturn, both of which promised extended exploration of gas giants and their moons. Uranus and Neptune, distant and difficult to reach, were pushed down the priority list. In the early 2000s, new mission concepts emerged. One idea was the Neptune orbiter and probe, which would have been modeled after Cassini and included an atmospheric probe. Although it gained some support, the cost and complexity proved prohibitive. Around the same time, Uranus missions were proposed in parallel, but they too faced the same challenges: long travel times, high expenses, and limited launch opportunities. The sheer distance to Uranus means that even with gravity assists, a spacecraft typically requires more than a decade to arrive, making such missions long-term commitments that demand both funding and patience. The strongest momentum for a Uranus mission came with the U.S. National Academy's planetary science decadal surveys, which set priorities for NASA's planetary exploration program every 10 years. In the 2011 decadal survey, Uranus was already highlighted as a compelling target. But other priorities, such as the Mars sample return and Europa Clipper, ranked higher. However, in the 2022 decadal survey, Uranus finally took the top spot. The report specifically recommended a Uranus orbiter and probe as the flagship planetary mission of the 2030s, citing its importance for understanding ice giants and their relevance to exoplanet studies. Several mission concepts have been fleshed out in recent years. The most widely discussed involves launching in the early 2030s on a heavy-lift rocket, such as the Space Launch System or Falcon Heavy. With a Jupiter gravity assist, such a spacecraft could arrive at Uranus in about 13 years. The mission would likely include an orbiter to conduct long-term studies of Uranus's atmosphere, rings, magnetosphere, and moons, as well as a probe to descend into the atmosphere and return data on its temperature, pressure, winds, and composition. The European Space Agency, ESA, has also studied ice giant mission concepts, though budget limitations make a joint NASA-ESA effort more realistic than an independent mission. Collaborative missions could distribute costs and allow for international contributions of instruments, similar to the Cassini-Huygens partnership between NASA and ESA. Japan and other spacefaring nations have occasionally expressed interest as well, though no concrete plans have been made outside the U.S.-European context. One major challenge has always been the power source. At Uranus's distance, solar panels are not practical, so missions must rely on radioisotope thermoelectric generators, RTGs, which convert heat from the decay of plutonium-238 into electricity. The limited supply of plutonium-238 has historically constrained mission planning, though recent production increases in the United States have made future RTG-powered missions more feasible. Ensuring sufficient power for a long-duration orbiter at Uranus remains a central consideration. Another issue is cost. A Uranus flagship mission is expected to require several billion dollars, placing it in the same category as Cassini or the Mars sample return. While expensive, advocates argue that the scientific payoff is worth the investment, given the unique questions only Uranus can answer. Furthermore, with the decadal survey backing and strong interest from the planetary science community, Uranus has never had a clearer path toward becoming a reality. Despite the long road, there is now a sense of momentum. NASA is studying detailed mission designs, and if funding is secured in the next few years, a launch in the early 2030s is possible. That timing is not only logistically favorable, but also scientifically advantageous, since Uranus will be approaching its northern summer solstice in the 2040s, offering an opportunity to study seasonal changes over decades. Looking back, the history of Uranus mission proposals is one of delays and missed chances. Looking forward, it appears the tide may finally be turning, with a strong scientific case, growing exoplanet connections, and prioritized recommendations. Uranus is now poised to take its place as the next great frontier in planetary exploration. Imagining a future Uranus mission brings up exciting possibilities. An orbiter paired with an atmospheric probe could transform our understanding of the planet and its system, providing data far beyond what Voyager 2 was able to gather during its fleeting flyby. Each component would play a unique role in piecing together the puzzles that make Uranus one of the solar system's most mysterious worlds. The atmospheric probe would likely be released months before the spacecraft entered orbit, plunging into Uranus's thick atmosphere to sample it directly. As it descended, it would measure temperature, pressure, wind speeds, and chemical composition at various depths. Current models of Uranus's atmosphere are largely based on remote sensing, which can only probe the upper layers. A probe could reveal whether there are deeper clouds of water, ammonia, or hydrogen sulfide, and how these contribute to the planet's weather systems. It would also determine the relative abundances of noble gases like helium and neon, which are crucial for understanding how the planet formed. Just as the Galileo probe revolutionized knowledge of Jupiter's atmosphere in 1995, a Uranus probe would provide a baseline for all future studies of ice giants. Meanwhile, the orbiter would carry a wide array of instruments designed to investigate nearly every aspect of the Uranian system. High-resolution cameras would map the atmosphere, capturing storms, cloud movements, and seasonal changes over the course of years. Infrared and ultraviolet spectrometers would study the planet's composition, tracking methane and other trace gases, and monitoring how sunlight and internal heat interact to drive weather. Magnetometers would measure the strange tilted magnetic field, clarifying its structure and dynamics, and showing how it connects to the solar wind. Radio instruments could probe the interior by analyzing how Uranus's gravity affects the spacecraft's trajectory, revealing details about its core and internal layers. One of the most anticipated targets would be Uranus's moons. The orbiter could perform multiple flybys of Titania, Oberon, Ariel, Umbriel, and Miranda, mapping their surfaces in far greater detail than Voyager 2's snapshots. Spectrometers could analyze surface ices and minerals, while radar instruments could search for subsurface oceans, much as has been done at Europa and Enceladus. Discovering liquid water beneath any of Uranus's moons would be a groundbreaking finding, opening new avenues in the search for habitable environments beyond Earth. Even if no oceans exist, detailed studies of the moon's geology would reveal their histories of tectonics, volcanism, and impacts, helping to explain why some are relatively smooth while others are scarred with rifts and cliffs. The orbiter would also revolutionize our understanding of Uranus's rings. Voyager 2 showed that they are dark and narrow, composed mainly of large particles, but much remains unknown. With modern instruments, the orbiter could map their structure with exquisite precision, identifying fine dust components, measuring particle sizes, and detecting how they interact with small shepherd moons. By watching the rings over time, the mission could determine whether they are stable or evolving, and whether collisions or ongoing processes are replenishing their material. Beyond the moons and the rings, the orbiter could provide continuous monitoring of Uranus's seasonal cycles. Because of the planet's extreme axial tilt, each pole spends decades in either sunlight or darkness. Voyager 2's flyby happened near the southern summer solstice, but a new mission arriving in the 2040s would capture Uranus near its northern solstice. Comparing the two seasons would offer an unprecedented view of how such extreme changes in sunlight drive atmospheric behavior. This kind of long-term observation is only possible with an orbiter, and it could reveal whether Uranus's storms and cloud systems follow predictable cycles or appear unpredictably. The magnetosphere, one of Uranus's most unusual features, would also be a prime target. With instruments designed to track charged particles, magnetic field lines, and auroral emissions, the orbiter could map how the tilted field behaves over time. It could reveal how the magnetosphere interacts with the solar wind and how it shapes conditions around the moons and rings. Such data would help test theories about magnetic field generation in ice giants, which may differ significantly from processes in gas giants like Jupiter. Importantly, an orbiter at Uranus would serve as a model for how to study exoplanets of similar size and composition. Many exoplanets discovered in recent years fall into the category of ice giants. And without detailed exploration of Uranus and Neptune, our ability to interpret exoplanet data remains limited. By revealing how Uranus's interior, atmosphere, and magnetosphere work, a dedicated mission would create a template for understanding countless distant worlds. In summary, an orbiter and probe combination could address nearly every major mystery about Uranus. Its composition, heat budget, magnetic field, seasonal atmosphere, ring dynamics, and moon geology. Such a mission would not just fill gaps left by Voyager 2, it would transform Uranus from a poorly understood outlier into one of the best characterized planets in the solar system. The payoff would extend beyond Uranus itself, influencing planetary science, comparative planetology, and exoplanet research for decades to come. Exploring Uranus is not just a question of science and engineering. It is also a matter of politics, budgets, and international cooperation. The cost and complexity of sending a mission to such a distant world make it unlikely that any one agency will act entirely alone. Instead, the future of Uranus exploration may hinge on global partnerships, where multiple space agencies contribute expertise, instruments, or funding to make the mission possible. Historically, large-scale planetary missions have benefited greatly from collaboration. The Cassini-Huygens mission to Saturn is a prime example. NASA provided the orbiter, while the European space agencies contributed the Huygens probe that landed on Titan. This partnership not only shared costs, but also gave the mission a broader base of support and a richer set of scientific capabilities. Similarly, ESA's Mars Express mission carried instruments from multiple countries, and Japan's Hayabusa asteroid missions have included U.S. and European contributions. These examples highlight how pooling resources allows missions that might otherwise be impossible. For Uranus, collaboration is especially appealing. The journey to Uranus requires a long-term commitment of funding, engineering, and planning that can span decades. No single agency has unlimited resources, and each faces competing priorities. Mars exploration, lunar programs, asteroid missions, and more. By working together, agencies can spread out the financial burden and ensure that the mission receives strong political support across multiple governments. International participation also increases the likelihood of maintaining funding over time, since more stakeholders have a vested interest in the mission's success. NASA is currently the most likely leader of a Uranus mission, given its experience with deep space missions and its prioritization of Uranus in the 2022 Decadal Survey. However, the European Space Agency has expressed interest in contributing. ESA could provide instruments, a probe, or even a spacecraft module, much as it did with Huygens. Japan's JAXA has also developed expertise in planetary missions and could play a role, particularly in instrument development or technology sharing. Even smaller agencies, like those in Canada or Australia, have contributed instruments to past missions and could do the same for Uranus. The politics of exploration also extend beyond funding and hardware. International collaboration raises questions about data sharing, leadership, and mission goals. Decisions must be made about which agency takes primary responsibility, how scientific data are distributed, and what priorities guide the mission. These negotiations are not always simple, but the benefits often outweigh the challenges. By involving scientists from around the world, missions can draw on a broader range of expertise and ensure that the results benefit the global scientific community. There is also a geopolitical dimension. Space exploration has historically been a stage for both competition and cooperation. During the Cold War, the United States and Soviet Union pursued separate planetary programs. Today, competition still exists, particularly between the U.S. and China, but there are also opportunities for collaboration. China has ambitious plans for space exploration, and while a joint Uranus mission between NASA and China seems unlikely given political tensions. It remains possible that other international partnerships could form, even if separate. Parallel missions are pursued, the overall scientific return would be amplified. Another political factor is timing. A Uranus mission requires a favorable launch window, ideally in the early 2030s, to take advantage of planetary alignments that allow for a Jupiter gravity assist. Missing that window could delay the mission by years or force the use of less efficient trajectories. This makes international coordination especially urgent. Agencies must align their funding cycles, technical planning, and political commitments well in advance to ensure that the opportunity is not missed. The politics of space budgets also play a role. Large flagship missions often come under scrutiny when national budgets are tight. Critics may argue that billions of dollars should not be spent on distant planets when pressing issues exist on Earth. Supporters counter that space missions drive technological innovation, inspire future generations, and often cost far less than many other government programs. International collaboration can strengthen this argument, since costs are shared and benefits are distributed among multiple nations. Ultimately, the politics of Uranus exploration reflect the broader challenges of deep space missions. They require vision, patience, and cooperation on a global scale. No single nation owns Uranus, and the scientific questions it poses are of interest to humanity as a whole. In that sense, a mission to Uranus would not just be about exploring a distant planet. It would also be a demonstration of what humanity can achieve when it works together across borders, pooling resources to push the frontier of knowledge farther than ever before. One of the most surprising lessons of the last 30 years is that our solar system is not the template we once thought it was. Astronomers have now confirmed over 5,500 exoplanets, with thousands more candidates awaiting verification. These worlds come in a dizzying variety of sizes, compositions, and orbital arrangements, many of which defy what our solar system seemed to suggest was normal. Among these discoveries, one of the most common categories of planets is what scientists call sub-Neptunes, worlds slightly smaller than Neptune and Uranus. That makes Uranus, along with Neptune, a critical point of reference in understanding the most abundant type of planet we know of. Uranus sits in a category that has been difficult to probe both observationally and conceptually. On Earth, we understand the distinction between rocky terrestrial planets and gas giants like Jupiter. But Uranus and Neptune represent a middle ground, sometimes referred to as ice giants. Their atmospheres contain hydrogen and helium like Jupiter and Saturn, but in much smaller proportions. Instead, a large fraction of their mass comes from heavier elements such as water, ammonia, and methane. This unique composition makes them an ideal analog for the sub-Neptunes that populate other star systems. By studying Uranus closely, scientists can test models of planet formation, interior structure, and atmospheric chemistry that can then be applied to hundreds of exoplanets. Exoplanet observations are inherently limited. Telescopes like the Kepler Space Telescope and the Transiting Exoplanet Survey Satellite TESS can tell us a planet's size by measuring how much starlight it blocks when it passes in front of its host star. Radial velocity measurements, obtained by observing the wobble of the star, can provide an estimate of the planet's mass. With size and mass together, astronomers can calculate density, which gives a rough sense of composition. But density alone cannot reveal whether a planet has a thick atmosphere, an ocean beneath the clouds, or an interior layered with exotic ices. This is where Uranus becomes invaluable. By exploring Uranus directly with orbiters and probes, scientists can ground truth the models that try to connect limited data with complex planetary realities. For example, many sub-Neptunes appear to have radii and masses similar to Uranus, suggesting thick atmospheres and volatile-rich interiors, yet others, with slightly different densities, could be rocky super-Earths with only thin gaseous envelopes. Without a clear understanding of what Uranus is truly made of, astronomers risk misinterpreting the data from exoplanets. By pinning down the details of Uranus's interior, how much of it is rock, ice, and gas, scientists can refine the way they classify and understand exoplanets across the galaxy. Atmospheric studies of exoplanets provide another connection. Telescopes like the James Webb Space Telescope, JWST, can analyze the spectra of starlight passing through an exoplanet's atmosphere during a transit. This reveals the presence of molecules such as water vapor, methane, and carbon dioxide. Uranus, with its methane-rich atmosphere, provides an ideal case study for interpreting such spectra. The planet's cold temperatures and unusual cloud dynamics give scientists a natural laboratory for testing atmospheric chemistry under conditions similar to many exoplanets orbiting far from their host stars. There is also a question of habitability. While Uranus itself is far too cold and hostile to support life as we know it, the study of ice giants helps refine the boundaries of habitable zones and the potential for moons or subsurface oceans. For example, Uranus's large moons may harbor liquid water beneath their icy crusts. If so, they could represent potential habitats, expanding the definition of where life might exist. In the exoplanet context, this teaches us that life may not require Earth-like planets. Instead, it could thrive in hidden oceans on moons orbiting ice giant analogs across the galaxy. The importance of Uranus in exoplanet science is also practical. Because sub-Neptunes are so common, astronomers will continue to find them in vast numbers. Yet, without a close-up understanding of what an ice giant is really like, we may spend decades mischaracterizing the most common type of planet. In that sense, a mission to Uranus is not just about our solar system. It is about building a foundation for interpreting thousands of planets in other systems. Planets that may one day dominate our understanding of the galaxy's architecture. Thus, Uranus is a key to bridging the gap between our own solar system and the wider universe. By solving the mysteries of Uranus, we refine the tools we use to study alien worlds and deepen our grasp of planetary diversity. In the age of exoplanet discovery, Uranus is not a distant curiosity. It is a Rosetta Stone for understanding the most widespread kind of world in the cosmos. Uranus, like every other planet, carries with it not only scientific significance, but also cultural and symbolic weight. From the moment it was discovered, it was named in a way that connected it to ancient mythology and the long human tradition of seeing the heavens as a place of gods and stories. While Mercury, Venus, Mars, Jupiter, and Saturn had been known since antiquity and tied to Roman deities, Uranus was the first planet discovered in the modern era, and its naming reflects a bridge between ancient myth and Enlightenment science. When William Herschel spotted Uranus in 1781, he originally proposed naming it after his patron, King George III. For a time, the planet was referred to as Georgium Sidus, the Georgian star. However, this idea wasn't popular outside of Britain. Astronomers across Europe preferred to keep planetary names rooted in classical mythology. Eventually, the name Uranus was suggested by German astronomer Johann Bode, aligning with the mythological tradition. Uranus, or Uranos in Greek mythology, was the primordial sky god, the father of the Titans, and a figure representing the heavens themselves. This choice maintained the continuity of associating planets with deities while acknowledging Uranus's position beyond Saturn, making it the symbolic father of the older gods. The mythology of Uranus carries themes of creation, distance, and cosmic rule. As the sky personified, Uranus was seen as vast and overarching, encompassing everything below. Yet he was also a figure of remoteness and detachment, much like the planet itself, distant, cold, and often overlooked in the night sky. The myths describe Uranus as both a progenitor of life and as a figure whose downfall was tied to violence when he was overthrown by his son Cronus, the Greek equivalent of Saturn. This mythological layering gave astronomers a poetic framework to place the new planet within the story of the cosmos. Culturally, Uranus has often been associated with change, disruption, and revolution. Part of this is historical. Its discovery came in the late 18th century during a period marked by political upheaval, the Enlightenment, and the Industrial Revolution. Astrologers in particular began to associate Uranus with sudden transformations, innovation, and rebellion against tradition. While astrology is not a science, the symbolic connection between Uranus and disruption has filtered into broader cultural context, shaping the way the planet is imagined even outside astronomy. In literature and art, Uranus has appeared less frequently than closer or more dramatic worlds like Mars or Jupiter, but its symbolism has nonetheless endured. Writers have sometimes used Uranus as a metaphor for remoteness or alienness, emphasizing its status as a far-flung world beyond the reach of ordinary experience. In speculative fiction, it has occasionally been imagined as a place of mysterious moons or strange atmospheric phenomena, though it has not captured the same degree of cultural imagination as Saturn's rings or Mars's deserts. Still, Uranus holds a unique place in cultural history because It represents the expansion of the known solar system. Its discovery broke the ancient boundary of Saturn, which for millennia had been seen as the edge of the cosmos. By pushing that boundary outward, Uranus symbolized humanity's ability to extend its vision and understanding beyond the limits that tradition had set. In that sense, Uranus became not just another planet, but a symbol of human progress and the infinite nature of discovery. The cultural resonance of Uranus also lies in the fact that it remains mysterious. Unlike the Moon, Mars, or even Saturn, Uranus has not been studied up close by orbiters or landers. Its relative obscurity keeps it in the realm of the unknown, a blank canvas for imagination. This makes Uranus a planet of potential. We know it exists. We know it has moons and rings, but so much is left unexplored that its story is still unfolding. In the future, as missions to Uranus are planned and eventually executed, it is likely that the planet will gain a larger place in popular imagination. Just as the images of Saturn from Cassini or the photographs of Pluto from New Horizons transformed public perception of those worlds, the first detailed portraits of Uranus's atmosphere and moons may inspire new waves of artistic, cultural, and symbolic engagement. Mythology will blend with science once again as humanity redefines what Uranus means to us, not only as a distant world, but also as a part of our shared cosmic story. The story of Uranus is not complete. In fact, it feels like it has barely begun. Despite being one of the largest planets in our solar system and a representative of a class of worlds common throughout the galaxy, Uranus has only been visited once, and that was a fleeting flyby by Voyager 2 in 1986. Nearly 4 decades later, our knowledge of Uranus remains full of gaps. We know its broad atmospheric composition. We have some crude measurements of its magnetic field, and we can make out hazy details of its moons and rings. But compared to what we know about Jupiter, Saturn, or even Mars, our understanding of Uranus is still at an elementary stage. This lack of exploration is one of the strongest arguments for why Uranus deserves a dedicated mission. A flagship mission with an orbiter and an atmospheric probe would revolutionize our understanding. An orbiter could map Uranus's magnetic field, study its seasonal cycles, monitor storms, and image its rings and moons in unprecedented detail. A probe could plunge into the atmosphere, sampling its gases directly to determine the exact proportions of hydrogen, helium, methane, and other components. Such data would finally answer long-standing questions about the planet's interior structure and formation. Beyond the scientific case, Uranus exploration has a symbolic importance. Each great planetary mission has marked a leap forward in our understanding of the cosmos and our place within it. Voyager gave us our first glimpse of Uranus, but it was only a snapshot. Cassini turned Saturn from a distant dot into a world of staggering beauty and complexity. New Horizons transformed Pluto from a blurry speck into a dynamic system with glaciers, mountains, and an atmosphere. Uranus awaits its turn. Bringing its mysteries into focus would continue humanity's tradition of expanding the frontier of the known. Timing is critical. The early 2030s provide an ideal launch window when a gravity assist from Jupiter can shorten the journey. Missing that opportunity would push a mission back by years or even decades. That urgency is one reason why the 2022 Decadal Survey placed a Uranus orbiter and probe as the highest priority for NASA's next flagship planetary mission. The coming decade represents a unique chance to commit to exploration that could yield results by the 2040s, giving a new generation of scientists and explorers a world to call their own. There are also broader implications. Studying Uranus is not just about Uranus itself. As one of the two ice giants in our solar system, Uranus serves as a key to understanding countless exoplanets. It represents the missing link between rocky worlds like Earth and gas giants like Jupiter. Unlocking its secrets will ripple outward, improving our ability to interpret planetary systems across the galaxy. It could also shed light on Earth's own history, since the processes that formed Uranus and its neighbors were part of the same grand event that shaped our planet. On a cultural level, a Uranus mission could inspire. Images of the planet, its tilted rings, and its icy moons would capture the imagination of people around the world. Discoveries of unexpected phenomena, whether strange auroras, hidden subsurface oceans, or new moons, would ignite curiosity and remind us of the endless surprises the universe holds. Just as Saturn's rings became an icon of beauty, Uranus could emerge as a new symbol of cosmic wonder. Exploration of Uranus also highlights the importance of international collaboration. The costs and challenges of such a mission are too great for one agency alone. By pooling resources, the global scientific community can ensure that this distant world is studied in depth. In that way, a mission to Uranus would not only be about science, but also about cooperation and the shared pursuit of knowledge. In the end, the case for Uranus is simple but profound. It is a world of extremes shaped by a violent past, tilted on its side, wrapped in methane, and surrounded by a system of rings and moons that remain largely unexplored. It holds clues to planetary formation, to the physics of magnetic fields, to the nature of ice giants, and to the diversity of worlds in our galaxy. It challenges us because of its distance and mystery, but that is precisely why it demands exploration. To ignore Uranus is to leave unfinished one of the greatest stories of planetary science. To explore it is to take the next step in humanity's long journey outward, continuing the quest to understand the universe and our place within it.